This session will be chaired by Naren from CMI. So over to Naren.
Thank you, Ayan. So maybe we'll wait like a minute more. Begin at 7:30 local time.
I see that David Gross woke up very early.
So while we wait for a half minute or something, so Nati, if you would like to take questions in between your talk, you could just pause at whatever time you feel appropriate, and you could take questions. Or if you would prefer to wait till the end of the talk, that's also fine.
I prefer to be interrupted.
So you would prefer to?
Anybody? This is a small crowd, so if anybody has a question, just yell.
Go ahead. Okay. Yeah. Sure. That's fine. Yeah. Great.
There is another option that people use in the chat, and then maybe somebody else can answer. So if the question, this is another way of addressing it. But if the group is small enough, then there's really no problem.
Right. Right.
Naren, maybe we should start because people
maybe we could
join.
start.
Yeah, we could start. Yeah.
Okay, so in this third session for today, day 4 of this conference, we are very happy to have Professor Nati Seiberg from the IIS Princeton. He's going to talk about fractons, going beyond standard QFT. Over to you, Nati.
Thank you. I first like to thank the organizers for putting together such an exciting conference and for inviting me to speak here. I'm particularly happy to give this talk in honor of David Gross. As one of the founding fathers of quantum field theory, I really hope you will sympathize with the motivation for this talk, fit fractons into his framework, mainly into quantum field theory. Now, I'll be talking about the number of papers that I've written recently with various collaborators, and some papers to appear. The second half of the talk is not yet published, so this is the first time it is presented in public. So let me start by way of introduction. There's a law in physics that starting at short distances with some lattice model with some short distance interactions, which are local, the low energy limit or the long distance limit is described by quantum field theory, by continuum quantum field theory. All the subtleties of the lattice at short distances are invisible by the time we go to long distances. And this law, although it was never proven rigorously, has been dominating condensed matter physics and to some extent quantum field theory over decades, which has been enormously powerful and enormously useful. And one of the applications of that, so it's not just that we have a description, this description in many ways is better than the underlying lattice model because it captures the universal aspects of the short distance theory. It does not depend on many of the details of the underlying theory. As an example, this is the difference between starting with a Riemann description of an integral as a sum and looking at the continuum integral where we don't need to have the discretization and results are independent of the discretization. So this has been enormously powerful, and I, for one, thought that it's always true, and this is a completely settled case until fractons showed up. And the history here is complicated. I'm not going to review it here. I would just say that fractons do not fit the framework of continuum quantum field. And I will soon elaborate why they do not fit that framework. So these are given as lattice systems, completely well-defined lattice systems, finite number of degrees of freedom, which are solvable. And once they are solved, you can look at the answer, and I will soon show that it's clear that the standard continuum quantum field theory cannot describe them. So as it stands, the law that I mentioned here, this law is just wrong. And this is very disturbing. The first time I heard about that several years ago, my first reaction was, this can't possibly be right. It can't possibly be right that this law is completely wrong. So this motivated us to try and fit fractons into the framework of quantum field theory. And it's clear that something will have to give. It cannot be a straightforward way to incorporate it. It cannot be completely straightforward. So we have to slightly extend the framework of continuum quantum field theory, but we shouldn't do it too drastically. The change should not be too drastic because we are in danger of wrecking the elaborate structure of continuum quantum field theory. So we'll be walking on very thin ice, trying to slightly extend what we mean by continuum quantum field theory, but we'll be guided by the lattice models. And there are really two motivations for that. One, for fractons, and the other for quantum field theory. For fractons, we would like to have a universal description of them, universal in the sense that something that captures the long distance behavior and is not sensitive to most of the short distance details. And by having such a framework, we'll be able to classify examples, maybe find more examples. We'll have a much deeper understanding of what's going on because our understanding will not be contaminated by all sorts of short distance details. And in the opposite direction, if we are going to extend the framework of standard continuum quantum field theory, this is clearly important for quantum field theory. And as many of us are interested in quantum field theory, this is a worthwhile effort. So let me say a few words about fractons. There are different examples and there are different characteristics. And let me focus on this slide on those models that are gapped. So the spectrum has a number of ground states, and then there is a gap, and then there are all sorts of excited states. And these are characterized by three things. All of them look very peculiar. First is that there are particles in the spectrum, particle excitations, with restricted mobility. These are particles that can sit at a point and they cannot be moved around. We can annihilate a particle at one point and create a bunch of particles elsewhere, but the one particle state cannot move. Other kind of particles are restricted to move on the line. They are called line knots because they can only move, say, along the x direction, but not along the y direction. Others are restricted to a plane. So that's the first peculiar thing, the restricted mobility. The second aspect I think is much more peculiar, is that I said that there's a finite number of ground states. That's true on the lattice, but if we take the continuum limit, namely, we introduce a lattice space in A, and the number of lattice sites, say we put the system on a lattice with periodic boundary conditions, so the number of sites, Li, big Li, goes to infinity with fixed size. This is how we take the continuum limit. There's no ambiguity, but this is the only meaningful way to do that. The number of ground states becomes infinite in the continuum limit. And not only infinite, it is typically sub-extensive, namely, it does not grow like the log of the number of ground states. So the entropy does not grow like the volume, but grows like the linear size of the system. This is very surprising in the context of quantum field theory, because it means that the number of ground states is infinite. I should also emphasize that in some models, this formula with the sum of the lengths is replaced by an expression which is much, much more complicated. And the number of ground states hops around between infinite, finite, infinite, finite. So adding one more layer of sites to the lattice, the structure of ground states is completely changed. So again, this is not something that can happen in continuum quantum field. The third aspect, which is intimately related to this one, is that the system has exotic global symmetries. And most of this discussion started its life in the quantum computation discipline, the discipline of quantum information and quantum information. And there they refer to them as logical operators. These are the global symmetries of the system. And the global symmetries will be quite exotic. I'll describe them soon. Now, this whole structure smells like something that some people, mostly in string theory, are familiar with, is UVIR mixing. The long distance behavior of the system, the study of the ground states is here, is very sensitive to details of what happens at short distances. The UV physics still contaminates the IR physics. And this is impossible in standard quantum field theory. On the face of it, it contradicts the picture of the renormalization group. The renormalization group is a way of hiding the short distance details in the long distance physics. And here, the long distance physics depends sensitively on such short distance details. So how are we going to address this question? So we're going to follow a three-step process. And let me first review the three-step process in the context of standard quantum field theory, so that everybody will have something to relate to, something to latch on. So we'll have three steps. In step one, we'll consider a meta theory which has a global U1 symmetry. In the context of quantum field theory, this is known on lattice models, it's known as XY models, where there is a phase into the I5 at every site. In continuum field theory, it's any model with a scalar field phi with what we would call momentum symmetry. I'm using the string terminology. Momentum symmetry, this is momentum in the target space, not in space, where we shift phi by a phase alpha. And there might also be winding symmetries. And all these models are gapless because this field phi is massless. So this field phi is massless, has a U1 symmetry, and that would be step one in our three-step process. Step two, we'll consider gauging this global symmetry. So we'll consider a gauge group being U1, the same as here. We'll consider it first a theory without matter, so it would be a pure gauge theory. So this would be a pure gauge U1 theory. And in this particular case, it means that we have a vector potential, a scalar potential A0 and a vector potential AI. This is completely standard. And since we have no matter fields, there is an electric, there are various higher form symmetry. There could be an electric symmetry and a magnetic symmetry. And the model is massless, is gapless, because the photon is massless. So this is step two. So step one would be a matter theory with a global U1 symmetry. Step two would be a pure gauge theory with a U1 gauge symmetry. In step three, we combine the matter theory with a gauge theory. We give phi charge n. So in the gauge transformation, there would be an n out here. And then as we couple it, the phi matter theory fixes U1 to Zn. And by doing that, it gaps the system. So we'll constantly have the three phases, and we'll go through, as we go through the talk, I will present three examples where we go through these three steps. And so altogether, we'll consider 9 models, the 1, 2, and 3. And then we'll have the same thing again for another model, and then the same thing again for a third model. And after we've done with all these 3 steps, we can use all our arsenal of techniques to use continuum field theory. We will look for duality. We will see that some of these examples are self-dual, some of these examples are dual to each other. For example, in 1+1 dimensions, this system is self-dual. This is known as T-duality. In 2+1 dimensions, this system is dual to that one. The single photon is dual to a compact scalar field. And there are other examples. So from this moment on, I'm finished with the introduction. So now we'll move to the modern work, and I'll show how we apply that in the context of a fractals. So Shuheng Chao and I embarked on the problem, and we looked at the lattice literature, the fractal literature. And the first thing you realize that most of the discussion there applies to Z2 spins. So they talk about Pauli matrices and so forth, and Z2 spins. But in order to have a good continuum limit, we thought we should start with U1. So wherever there was a spin there, we put a phase. So in step 1, we consider a matter theory. And as a copy from the previous slide, this is an XY model, or put a phase into the I5 in every site. And then these models end up having interesting subsystem global symmetries. So this is the first time in this talk that we have something peculiar, where the field phi can be shifted not by a constant, by an arbitrary function of x plus an arbitrary function of y plus an arbitrary function of z. This is a huge it's a global symmetry. So the Hilbert space is a representation of this symmetry. And that's what it is. So it's a very large global symmetry. Now we move to step 2. We want to gauge this symmetry. So as we gauge this symmetry, so we're going to find a gauge theory whose gauge parameters satisfy this group transformation. And typically we're going to find scalar potential K0, and it's in the spatial components of the gauge field we have 2 indices, symmetric 2-index tensor. And again, there could be electric and magnetic subsystem symmetries. This thing mirrors what we do in ordinary field theory. In step 3, as I said before, we take phi from here, and we use it to Higgs A from here, and we Higgs U1 to Zn, and by doing that, we find the gap system. And as in the continuum, we study these models now in a lot of details because we are new, so every detail has to be checked. And once we have the continuum model, as I said before, we have the whole arsenal of techniques of continuum quantum field theory. We look for dualities, and they turn out to be very interesting. And once we have all these continuum models, we can start extracting information from them. So the first nice thing that we will see is that all these complicated lattice models that people have been studying end up being free field theories. So from this moment on till the end of the talk, all the field theories that we'll be discussing are free fields, are completely free fields, or in technical terms, they're called Gaussian. And as such, they should be straightforward to analyze. As we will see, there are many subtleties, but we don't have any subtlety of renormalization. We don't have any subtlety of interactions, because all the models are free. Our Hilbert space can be, the Hamiltonian can be diagonalized exactly. The Hilbert space can be completely characterized. So this thing really hides where the subtleties are, because the Lagrangians that we will study are non-standard Lagrangians. And as such, the analysis will be quite subtle. And one question we will ask ourselves is, what is the meaning of these Lagrangians? I will write very complete continuum Lagrangians, but we'll have to address the question of what is the meaning of such a Lagrangian? What is the appropriate space of fields? As you will see, the main point would be that the main reason these models are peculiar is that we'll have to think about discontinuous fields, fields which vary discontinuously from point to point in space. Now, on the lattice, everything is discontinuous. If we move from one side to the other, the degrees of freedom are totally unrelated. Only the Hamiltonian relates them. So the fields that we look at here will be more continuous than on the lattice, but less continuous. Sorry, would be more continuous than on the lattice, but less continuous than is common in standard quantum field. And the fact that we will have such discontinuous fields, high derivatives can be important. And that yet some universal behavior remains. So the peculiarity of UV-IR mixing that I mentioned earlier is really related to the fact that we have to study discontinuous field configuration. So what happens at the point where the field jumps, that is sensitive to the UV, but we will see that nevertheless, there is some universal behavior that we can extract. Some of the continuum field theory that we will find will be robust in the sense that we can, once we are done and we found the system, we can twiddle the short distance theory. This doesn't make a difference. Or another way of saying it, all the operators that preserve a certain global symmetry in the long distances will end up being irrelevant operators. So the system will be stable or robust. And we will also see that we have a lot of dualities that are easy to establish in the continuum, relating our theories to each other. So now let me be a little bit more technical. We are not going to preserve the full SO3 system, the all SO3 rotation symmetry, but only the cubic group. So the cubic group of the symmetry group of the cube, not counting reflections, is isomorphic to S4, the permutation of 4 elements, and it has these kind of representations. This is a scalar of SO3. This is a vector of SO3. And the other 1', 2, and 3' are other representations of S4, which originate from higher spin of SO3. And we studied examples where the matter field phi is in any one of these. After all, if we want to preserve only S4, we can put the fields in whatever representation of S4 that we need, and we are free to put it wherever we want. We can also consider the field to be periodic. In fact, I said that we would like the field to be a phase. So we would like some periodicity phi is identified with phi plus 2 pi. And if we have several fields, like if we are in any one of these representations, there are more sophisticated identifications of the field that are allowed, and I will describe that soon. And then we're going to write a Lagrangian that preserves only S4. So there will be derivatives, the way we normally write derivatives, but the indices will be contracted in a way that preserves only the S4 subject. So it will be d by dx and d by dy, and this will put some restriction on what the kind of terms that we can write in the Lagrangian. And of course, we can change the symmetry group to be a different subgroup of the rotation group or no symmetry at all, and we'll see exactly that. So let me move to the first example. This is the model that was analyzed on the lattice by these three people with a lot of follow-up. And this is an XY plaquette model. XY because the variables are phases, and we put a phase at each site of the lattice. And we also put the conjugate momentum at the site. And the interaction is product of these phases equal to I phi around plaquettes. In the standard XY model, the interactions are across links. The field here times the dagger of the field here, but here we'll multiply phi's across plaquettes. So the model turns out to be gapless. It has a massless field phi. Phi is massless in the continuum limit. And then we can just expand the Lagrangian, the lattice Lagrangian continuum, neglecting higher derivative terms, and this is the Lagrangian. And as I promised you, the Lagrangian is free in the sense that it's quadratic in the field phi, and therefore it should be straightforward to analyze it. There are no first derivative terms. This is related to the fact that we do not have interactions across links, and the plaquettes lead to these double derivative terms. So that's non-standard. And you can also see that it preserves only S4 because we can pollute X, Y, and Z, but we do not have continuous rotation. And this model has this peculiar global symmetry. It's called the subsystem symmetry, when we can shift phi by an arbitrary function of X plus an arbitrary function of Y plus an arbitrary function of Z. And it's straightforward to check that this Lagrangian is invariant under this global symmetry. And if we want to count how many parameters we have, we temporarily put the system on a lattice, and we have Lx parameters in the global symmetry here, Ly parameters in the global symmetry from here, and Lz parameters in the global symmetry from here, and we have to subtract 2 in order not to count the 0 modes too many times. Now, let's study this system a little bit. This is the Lagrangian, and we can substitute here phi, which is an arbitrary function of x and t. And this function of x can be a discontinuous function. Normally, terms like d by dx phi squared suppresses such discontinuous configurations. But in our case, they are not suppressed, and they can exist in the continuum limit. So our continuum limit necessarily includes field configurations that are discontinuous. But we should be such that dx dy phi should be well behaved. So dx phi might not be well behaved, but dx dy phi must be well behaved, because if it's not, this term with the Lagrangian is going to suppress it. And there could also be higher derivative terms that are equally important as the terms that we included, and they might affect universality, but it turns out that they do not change the qualitative features that I will describe. Now, this is very reminiscent to the ordinary compact boson saying one dimension in 1 + 1 or 2 + 1, etc., which also has a winding symmetry. The underlying lattice model does not have the winding symmetry, but the continuum system often has such winding symmetry. And the interesting winding configurations are written here. And notice that we have separate winding charge for every point x and every point y, and every point z. And these are the winding charges where we integrate various quantities. These are total derivatives, and they lead to a delta function. Now, at this point, if you are very quick, you can notice that if we substitute this Lagrangian into this configuration in this Lagrangian, then the action is infinite. And therefore, strictly speaking, such configurations are indeed suppressed in the continuum limit. But I want to mention them here anyway, because they will play an important role later. One can also study this system, including these configurations, and this is interesting on its own right. So this is the end of my analysis of step one in the three-step process, where we discuss only the phi system. And now let's move to the gauge theory. So the relevant gauge theory is based on early work on tensor gauge theory by Shu and followers. In relation to fractons was identified by Pretko. And we'll study a variant of the gauge theory that these two papers studied that first appeared in the work of these people. And I'll present my version of this discussion. So these are the gauge fields. We're going to have A0, that's standard in gauge theory. But for the special components, we're going to have three fields, AXY, AXZ, and AYZ. We're not going to have AI, which has a vector index, because every special field will have two indices. And the gauge symmetry is written here. A0 is identified with A0 plus D0 alpha. That's in the one dimension. This is the scalar representation of SO3, and it's also the scalar of S4. But the spatial components are not in the vector, they are in this representation called 3 prime. And we can form gauge invariant combinations of these gauge fields. We have electric field and magnetic field, and I wrote them explicitly, and I also wrote their S4 representation. I don't expect people to hear that for the first time. I don't expect them to follow all the indices, but what I do want to convey is that this is very, very explicit. Right, very explicit formulas. You can write it in components. There's nothing subtle in doing that, and I'm not hiding anything. And then we can write a Lagrangian, which is E squared minus B squared, and we can analyze the spectrum, and the spectrum includes a massless photon. I put photons in quotation mark because it's the component, the field is this Aij rather than AI. So here we just follow our nose and do what we normally do. Now, Pretko noticed something very interesting about this system. If we add matter fields to it, Gauss' law is obtained by taking the derivative with respect to A0, and that some derivatives acting on E is the charge density. So if we are in non-compact space, charge is conserved, but also the dipole charge is conserved, because if you substitute this in here and you integrate by parts and just do good behavior with infinity, both the charge and the dipole charge are both conserved. And therefore, if we have a particle that carries charge, it cannot move. We can move it and preserve its charge, but that would destroy the conservation of the dipole charge. I would like to phrase it a little bit differently. So first of all, this is the origin of the restricted mobility of these fractons. And I would like to phrase it a little bit differently in a way that makes sense, also in the theory without matter fields at all. And also if we just work on compact space, in finite volume or periodic boundary conditions. So in the pure gauge theory without matter, we normally consider defects. So all the charged particles are represented by defects, and the defects are integral along time of A0. So instead of thinking of dynamical matter, we think of the dynamical matter as being very heavy. These are 12 particles, and we have such a particle. Now, normally, we can bend the defect and let it move in space by using AI. But this system doesn't have AI. So this defect cannot be bent, cannot move in space. So we analyze this system in a lot of detail. And again, we need to consider it very much like in the matter system. We need to consider discontinuous field configurations and discontinuous gauge parameters. And when we do it carefully, we realize that as in ordinary gauge theories, we have quantized fluxes. They are kind of characteristic classes associated with that gauge theory. And the system has subsystem electric symmetry, and in the continuum, we also have a magnetic symmetry. And this theory actually has a peculiarity in the continuum that is not there on the lattice, is that the lattice theory can be destabilized by monopole operators, very much like U1 gauge theory in 2+1 dimensions. The Polyakov mechanism tells us that we have monopole operators. These, even if we assume that the photon is massless, the monopole operator is typically relevant in the continuum limit. And if the underlying lattice system does not have a magnetic symmetry, we cannot suppress it. And as a result, the system is gapped and it's not robust. In this case, however, the monopole operator turns out to be very relevant. Its dimension goes to infinity in the continuum limit. And therefore, this system is actually robust. So this was part two. Part one, we analyzed the matter system. Part two, we analyzed the gauge theory. In part three, we tried to Higgs the U1 to Zn and thus gap the system. So there's various ways of thinking about it. I like to think of the Higgsing as adding field phi with charge n and adding to the Lagrangian such a term with the Lagrange multiplier b and such a term for the spatial component with the Lagrange multiplier eij. So the gauge transformations of the gauge fields are as before, and phi has this gauge transformation, and you can check this gauge. If you don't like this picture with Lagrange multipliers, you can drop this b here and put square here, and you can drop this e here and put square here. So this would be the standard kinetic term of a Higgs system. So now we have Higgsing, and we can now do a lot of things very easily in the continuum. One thing, phi is a compact scalar field, so we can dualize it. If we dualize it, we find the BF type description of this system. We have the fields that we had before, which I denote by A, and the electric and magnetic fields are this B and this T. And we have other exotic gauge fields, which I denote by A hat. So this is a BF description of the same Higgs system. So this is very similar to what we do in ordinary gauge theory. And the parameter here, the coefficient n, is quantized because of large gauge transformation. This is again very similar to what we do in ZN, or standard ZN gauge. And this system has defects. The simplest one is just fractal. This A moves along a straight line in time, and it cannot bend in space, and therefore this particle is localized at time. It's very similar to what we had in the U1 gauge theory. The same thing is true in the ZN. It also has various dipoles that we can study, so we can write a gauge invariant defect. So a single particle cannot bend, but a dipole with one particle at x1 and the antiparticles at x2, they can move in the y and z direction, but they cannot move in x. So this dipole is a planar. And the restricted mobility again follows from the gauge symmetry. Now the system has more defects coming from winding operators of phi, or equivalently from Wilson lines of A hat. And all of them can be analyzed in a lot of details. And you will soon see what this picture corresponds to in the fractal literature, and it matches. The next thing we would like to study is the spectrum of the system. That's very easy in the continuum language. The way we will do that is we'll specify phi. So for every phi configuration, we can solve for A to set this to 0 and to set this to 0. We just substitute A equals 1 over n di dj phi and A0 to be 1 over n d0 phi. So we solve. And then the ground state at the space of phi's modulo gauge transformation. And these are the non-trivial functions that generate this space are precisely the winding modes I described earlier. So for every value of x0 and y0, we have a winding mode of phi, and correspondingly, we have a ground state of the system. So for every value of x0 and y0, we have an integer modulo n, because if we put an n out front, we can remove it by a gauge transformation. And if we add the other directions, and we account for the common zero modes, the number of ground states is this formula. So the number of ground states diverges exponentially in the continuum limit, and it diverges in a way that is linear in the size of the system. So that's the number of ground states. And as we said, we have only zero energy states. The system is gapped. And we can work out all the gauge invariant operators that act there. These are various Wilson lines for this funny gauge theory. And the spectrum turns out to be in the simplest representation of this algebra of operators. Now, our system does not have any local operators, and therefore it is robust. It cannot be destabilized. So I've presented it by starting from the matter system, then I studied the U1 system, and then I Higgsed it down to Zn, and I analyzed all the properties of this theory in the continuum. And that's actually one of the most commonly studied model in the fractal literature. V.J. Hein Fu studied a model known as the X-cube model. They studied only the n=2 version of it, and we have a Zn version of it. But the main point is that we have it in the continuum, and all the peculiar results that I presented match what was obtained on the lattice for n=2. For people who are familiar with ordinary Zn gauge theory in 2+1 dimensions, this is one of the most common topological field theories in 2+1 dimensions, I prepared a table that shows the similarity and the dissimilarities between 2+1 dimensional Zn gauge theory and this tensor Zn gauge theory in 3+1 dimensions. So this column is an ordinary gauge theory, and it is in 2+1 dimensions. This is this tensor gauge theory in 3+1 dimensions. The Lagrangian in both cases can be described as U1 going to Zn, or we can Higgs, or we can dualize the Higgs field, or the Stuckelberg field, to a hatted field, and the same thing is true here. So these two are very similar. The phase is gapped, and it is robust in the sense that there are no local operators. The defects and the operators in this theory are Wilson lines of A and Wilson lines of A hat. The same thing is true here, but we have to consider lines and strips. But all this structure is completely determined by gauge invariance. Here, the particles are anyons, and that's why there is interest in these systems. Here, on the other hand, the particles are fractons, linons, or planons. These are these particles with restricted mobility. In the gauge theory, we have n square states on the torus. The holonon is around the A cycle and the B cycle. And here we have n to a power, but the power diverges in the continuum. So this is the end of what I wanted to say about this system. And in the rest of the talk, I will describe two other systems. So this would be a nice place to pause for the question. So just yeah. No questions, it means that either I lost everybody or it was crystal clear. Okay, I take the crystal clear and I will continue. So the next model that we studied is an anisotropic model. So it's not going to have even a S4 symmetry, but a much smaller point symmetry group. And similar models were studied in the condensed matter literature by these people. So I'll present the continuum descriptor because after what we have done, it will be straightforward. And the description will follow the same three-step process. And I'm going to start with the matter system and then the U1 gauge theory and then the Zn gauge theory. So what I'm going to do is write in the Z direction standard kinetic dz phi squared. And in the X and Y direction, I'm going to play the same game we played before, have only dx dy phi squared. So we're not going to have dx phi squared. We're not going to, we can also have higher derivatives, dx dz, but this would be the dominant one in the Z direction. So in a way, this system is simpler than the previous one because in the Z direction, it behaves like an ordinary theory, but in the X and Y directions, it has this peculiar behavior. And again, we are going to identify phi with phi plus 2 pi. And as in the previous example, we have a very large subsystem symmetry. We can shift phi by an arbitrary function of x plus an arbitrary function of y. You see this term and this term are trivially invariant. In this term, usually the d by dx phi ruins this symmetry. But now this term is absent. So this term is invariant under this large global symmetry. And as in the previous example, we need to study discontinuous fields and winding symmetries and winding modes, etc., etc. So it's straightforward but tedious, and we just did it. Next step, we should study the corresponding U1 gauge theory, the U1 gauge theory in which this global symmetry is gauged. And that might look horribly complicated, and it is, but I emphasize that it is straightforward. So this is something you just follow your nose and you find what you need to do. There's a gauge symmetry alpha. A0 transforms in the standard way. There's one gauge field associated with the Z derivative of alpha. And then there's another field which has the dx dy function. And we can form gauge invariant combinations of these guys. And this gauge theory turns out to be gapless, because this photon that we described here is actually massless, and it has various electric and magnetic high form symmetry or subsystem symmetries. One surprise that we face already here is that the matter system that we discussed before is actually dual to this U1 gauge theory. This U1 gauge theory is dual to the previous U1 system that we studied. This is very similar to electrodynamics in 2+1 dimensions, where the U1 gauge theory is dual to a compact scalar field. Now, the next third step, so we said first step one was matter system, step two was the U1 gauge theory, step three, we Higgs U1 to Zn, and we find a Zn gauge theory based on this peculiar gauge symmetry, and it turns out to be gapped, because as always, when it's Zn, it's gapped. And we can use duality. We've already said that the matter theory is dual to a gauge theory, and we can find the BF type description of this system. And it turns out that this Zn gauge theory is the continuum limit of a gap model of fractons that was studied in the condensed matter literature by these authors. And we matched everything that can be computed on both sides. So the lattice here, we use the lattice as a way of checking. It's kind of a sanity check that we know what we are doing. And I'm very pleased that we can reproduce all these results by writing a continuum Lagrange with some well-defined rules how to deal with these derivatives. I should say that when I talk to condensed matter people, they always look at every one of our results and they ask, can I do it on the lattice without ever mentioning the continuum? And the answer is, so far, of course, yes. Some of the dualities are not so easy. Some things are easier in the continuum, but that's not the point. The point is that we can do everything in the continuum, and then, as you will soon see, we can derive new results in the continuum that had not been derived earlier in the lattice description. So this is the end of the second example. Again, 3 steps: matter, U1 gauge theory, and Zn. And now we would like to make this anisotropic model isotropic. This will be the third example. Now, we're not going to make it completely isotropic under SO3 rotation, but we're going to preserve the S4 symmetry of the S4 symmetry of the cubic lattice. So we started from this Lagrangian, standard in the Z direction and non-standard in the X and Y direction. So it's trivial to make it isotropic. We just copy this system 3 times. We call this field phi Z. And now we add same Lagrangian with phi X and the same Lagrangian with phi Y with appropriate relabeling of the coordinates. That would make the system isotropic, but isotropic in a trivial way because it's really 3 decoupled systems. So in order to couple these 3 systems, we would like to make it the coupling between them as mild as possible. And we do it by gauging the Z2 times Z2 sub. We're going to have 3 fields, phi X, phi Y, phi Z, in the 3-dimensional representation of S4. And we have funny periodicities. Every one of them is identified with 2 pi times n. But these n's can be either integers or half integers, provided the total sum of them is an integer. So again, it's the same as the previous model, and the only difference is that in various twisted, when we quantize momentum or winding, we'll have to worry about this correlation between the different modes. So it's straightforward to analyze this model, and I'm kind of repeating myself. The system is gapless. There are 3 massless fields, phi X, phi Y, phi Z, and we have some global symmetries, some subsystem global symmetries. And then we should ask ourselves, is this a new model or is this something that is already out there in the literature? And the answer is that this model was actually studied by V.J. Hai and Fu. They considered a system on an FCC lattice. So since most of you are high energy physicists, I should explain what an FCC lattice. Take an ordinary cubic lattice, which has all these black dots on it, and which has all these X dots on it. I think I lost my pointer.
So I have a small question, actually.
Yeah, please.
Yeah, your Lagrangian, the time and space are asymmetrically scaling or what? They have different
They're
dimensions?
not symmetric. I treat space and time differently.
I see. So do you need more parameters, or this is some?
There are more parameters. I can add more parameters. In this Lagrangian, I suppress the parameters, but we can study everything as a function of the parameters.
Okay, thank you. Thank you.
Yeah, thank you for the question. So I hope this pointer will work. So we have an FCC lattice, so it has some corners, like in a cube. And in the middle of every face, we put another dot. So red here and here, green here and here, and blue here and here. And we can connect them by tetrahedron. So that's an FCC face-centered cubic lattice. And the interaction, so we put an XY spin at every side of the lattice. That's very standard. And the interaction is product of spins around the tetrahedron. So we don't have interactions along the edges here. We also don't have interactions along the nearest neighbors, but we have around these tetrahedron. And if you look at this model in the continuum limit, it turns out that this is our model. This is exactly our model. And something wrong with my pointer. This is exactly our model. Our model is the continuum model that I wrote, is the continuum model of the lattice model that these people wrote down. I think, oops, yeah. So this was the matter system. The next step, we study the gauge theory. So we repeat the same steps, either gauge the previous system, or we couple the anisotropic model. We have 3 copies of them, so we couple them, and we find the U1 gauge theory. And again, it's gapless. It has a subsystem, electric and magnetic global symmetry, and it's dual to what we had before. So the whole system, the whole situation, is, as I said before, is reminiscent of what we are used to in 2+1 dimensions, that the phi system with an ordinary global U1 is dual to a U1 gauge theory. So this is an ordinary quantum field theory that you study in quantum field theory 101 or whatever quantum field theory course you study. There is such a duality. The same thing is true for this particular gauge theory in this particular matter system. Now, this system actually has a very nice lattice description, which is also in the literature. It comes under the name of the checkerboard model. And we put the gauge theory as follows. The gauge parameter is set at the centers of the shaded cubes. So not every cube, but every other cube. And the gauge field is at the sides of the checkerboard. And the interactions associated with them. So, and this is very, very similar to the FCC description, because this checkerboard is the center of the cubes of this checkerboard are the same as the sides of the FCC lattice. And the reason I emphasize it here is that this discussion is not some completely decoupled analysis of arbitrary continuum models we can write down, which is connected to models that condensed matter people are interested in. Now we can consider the ZN gauge theory. This is step 3 in our steps. Again, the matter theory, the U1 system, and the ZN. So we use the matter system with charge n to Higgs, the U1 to Zn. The system is gapped, and we have various dual descriptions because we can have a BF type description of this system. And using this continuum description, we can show, it's straightforward to show that for n equals 2, remember we have a Zn gauge theory, then for n equals 2, this system is actually dual to 2 copies, 2 decoupled copies of the X cube model that I presented earlier. So this model for n equals 2 is 2 decoupled version, 2 decoupled sectors. Each of them is a Zn tensor gauge theory. In the Fracton terminology, the checkerboard model, the Z2 checkerboard, is 2 copies, 2 decoupled copies of the Z2 X cube model. But what is also clear from the continuum is, so first of all, we have a clear derivation of this, which is completely straightforward, but also this is not true for higher n. So for higher n, this is actually a different model. Now, this Zn system that I presented is the continuum field theory description of a Zn version of the checkerboard. So these people studied the checkerboard model, but they studied only Z2. What I presented here is a generalization for n. But in the fact that for n equals 2, the model of these people is 2 copies of the x cubed model had been known before, but what we've done here was to find the Zn version of it and to show that the Zn version of it is not simply related to copies of the Zn version of the x cubed model. We also exhibited the relation between the anisotropic model that was studied sometimes by the same people and this checkerboard. So we have a whole zoo of models that these people studied, and they're a lot easier to think about in this coherent fashion using this continuum field theory. So let me summarize the talk. Fractals exhibit interesting properties. For me, the most interesting thing is the UVIR mixing, telling us that the naive picture of the renormalization group is not quite right, and some UV behavior can contaminate long distance physics. We have a large ground state degeneracy. Sometimes the degeneracy diverges in the continuum limit, and sometimes there isn't even a well-defined formula as n goes to infinity because the number of ground states hops around. And the observables can be discontinuous. And that's what the fractals do, and our continuum models reproduce all that. The second peculiarity is that we have excitations with restricted mobility. And again, this is very strange, but our continuum description reproduces it as a consequence of the gauge symmetry of the system. So I emphasize many times that these peculiar properties are incompatible with the framework of continuum quantum field theory. But we presented a non-standard continuum quantum field theory that does all these things. It's invariant only under discrete rotations. I don't think this is essential. Well, it is essential for these examples, but that should not surprise any quantum field theories. We often study quantum field theories that are not invariant under continuous rotations. It exhibits these exotic global and gauge symmetries. These that depend on position, so these subsystem symmetries. And that's perhaps the most interesting fact, is that the fields and the gauge transformation parameters can be discontinuous and even singular. But as I said, they are more singular than in standard continuum field theory, but they are more continuous than standard lattice systems. And the main advantage of these continuum field theories is that they capture the universal behavior of the lattice system. And by that, I mean that they reproduce all the long distance physics and the properties of Paul particles. Now, on the lattice, the model is interacting. Some aspects of it can be analyzed exactly, some of them are not. And one might be nervous. What happens if you distort the system a little bit? Our system is described, our field theory is free. So it's quadratic in the fields. And it's really straightforward to analyze it, except the subtleties associated with the discontinuous field. So it is subtle, but in a different direction than the standard subtleties of quantum field theory. I would like to end with some outlook. The first thing that I think needs to be done, and I've already alluded to that, is to make the treatment of the discontinuous field configuration more precise. And we have made some progress on that, and we are writing a paper about it. The second thing, we need to understand better the underlying geometry of these gauge theories. What are the characteristic classes of them? How should we think of twisted bundles in more detail than what we did? What we did was very lowbrow. I'm sure this can be stated much better. We like to place these theories on more complicated manifolds. Here, there's a lot of work in the condensed matter literature saying that the model cannot be placed on an arbitrary manifold, but we need to put on it also more structure, and in particular, we need to put some foliation on the manifold, which will give us these special subspaces associated with the subsystem symmetry. And again, I have a lot more to say about it, but I don't have time for that. I would like to repeat that for all the known lattice models. So currently, I'm going through the condensed matter literature, the fractal literature, trying to see whether every single phenomenon they found, every single model that they have, can fit this description. In previous times, I gave these talks, including in India. I described only the first class of models. And today I describe two new classes of models that exist in the condensed matter literature, and we cast them in our framework. So I think it's very important to stay with this being connected to the lattice discussion, because this will give us kind of a reality check or a sanity check. And also we want to make sure that we are not going in the wrong direction. And I think we should find more models. In fact, we've already found more models, and I presented you new models that had not been found earlier in the condensed matter literature. And I think that what is really within reach is to formulate all these models in a coherent framework. And I think that the continuum description that we have will give us a nice setup to describe all these models, just as we usually do. Like in topological field theory, we have various ways of thinking about it, as a transaminance theory, modular tensor category, and so forth. We should find the same thing here, because it's clear that these models are generalizations of topological field theory. They are somewhat topological, but not completely topological. So from my perspective, this is the next step after topological field theory. And for all these reasons, I find this enormously exciting. So since my time is up, I'd like to thank you all, and please stay here. Thank you.
Let's all unmute ourselves and thank Nati for a masterful talk. Questions and comments?
I have a question.
Yeah, go ahead, please.
So, very nice talk, Nati. I have a question. Do you envision fractons as arising as some phases in standard quantum field theories, or there's a no-go theorem for that?
This is a fantastic question, and I wish I knew the answer. And I think that the only way to move toward it, so I think this is very important to understand, whether standard field theory, which has ordinary symmetry, can produce such a thing at long distances. So I'll give you two answers. Well, three answers. The first is phenomenal. The second answer is that some of these models are robust. So if you took a standard field theory and you tuned the parameter, and you landed on this theory, on this phase, the same will be true in some finite neighborhood in coupling constant space in that field theory, because these models are robust. So so imagine you tune the parameters, you tuned, I don't care, 1 billion parameters, and you landed on that point. If you landed on that point, you could ask, what happens if I don't tune, if I change the parameters? The way to think about it is to go to the long distance physics and to identify all possible deformations there. What are the relevant operators there? Well, these systems, some of them at least, do not have relevant operators. So if you were lucky and you found that point, this will be true in a finite neighborhood around this point. So in that sense, it's very likely to happen. But the third answer I would give is that the way to address that is really work out more examples. So instead of thinking broadly, what can you possibly do? I think what we should just do is work out many, many examples, hoping that some pattern would emerge. And it's already, we have some kind of a pattern that emerges, but we still have a lot of scattered results.
Thank you.
Other questions?
Can I ask one question too? About the first model, that Nari presented?
Go ahead, please.
Yeah, so if you allow discontinuous configurations and you add arbitrary higher dimensional operators, how do you treat the various finite delta function singularities that would pop out?
Very good question. So if we consider so some of the operators that we have if we put higher derivatives, these operators will be important at long distances. So we should explore what they do to the answer. So in the gapless phases, they change some of the quantitative answers, but do not change the qualitative answers. And in the gapped phases, they don't even do that. Now, let me compare that with the situation that many of you are familiar with. Let's consider a supersymmetric theory that has flat directions. So we work at the origin. This is a field theory. The theory at the origin has a lot of operators that take us in the other direction, along the flat direction. Now, some of them end up being exactly irrelevant, because we can just move in that direction in space. And if we move, so we try to move in the other directions, and various operators that are irrelevant at the origin become relevant along the flat direction. Example, consider a field theory that has a potential 5 to the 10th. 5 to the 10th is irrelevant in the origin. It's an irrelevant operator. But we know that it is very important because if we drop it and we move along the flat directions, 5 to the 10th pushes us back in. It becomes relevant to the flat direction. And if there is a genuine flat direction, various operators that do not lift it change the masses, for example. So even though if you sit at one point, there is a finite number of relevant operators, as you move along the flat directions, other operators, which will be relevant to the origin, become relevant along the flat direction. So in order to completely specify the long distance physics, it's not enough to specify the physics at one point in field space, but you need to explore other regions in field space also. And the same thing is true in this case. Now, more mechanically, we're going to get all sorts of delta functions, and we'll have to multiply that. And we need some kind of a calculus to treat all these derivatives of delta function and so forth. And most of the work in the series of papers that we wrote, and I completely glossed over that aspect in this of the story in this talk, most of the work was to get straight this particular story. How do we think about configurations that are discontinuous, and yet we keep them in the continuum theory? Because there are also delta functions and delta of zero. What do we keep, what we don't keep, and how do we ensure that we land on our feet? So since I have one more minute, let me just give you a hint of what's going on here. On the lattice, everything is meaning. There's no delta function, no divergence, everything is finite. So we need a rule which configurations from the lattice we allow and which configurations on the lattice we do not allow. And we have a way of describing it. It's kind of a funny gauge theory associated with the periodicity of the fields, which tells us exactly which singularities are tolerated and which singularities are not tolerated. And then it's a real challenge that if we work in this space of functions, and we start multiplying functions, taking derivatives, taking linear combinations, and so forth, we stay within this space of functions that we are interested in. And most of the work that we have done was indeed to get this particular aspect of the story straight. I did not say a word of it here. And honestly, I feel that this can be stated in a much, much better way than we presented it. But on the other hand, I'm quite convinced that the story is right, because after all, the lattice models exist, and the lattice models have answers. So there is a well-defined finite answer, and what we're trying to find is a continuum field theory description of the known answer. We're not trying to build something completely crazy. Once we have it, we can go back and try and extend the boundaries a little bit and do more than was done on the lattice. I hope this answers your question.
Other questions, comments? So I had a question, Nati. Can you anticipate how deep-brain constructions of any of these models might work?
Okay, the answer is no, but I'll rephrase your question in a broader way.
Yeah, please.
I will still not be able to answer it. I think what you really have to is, we studied the system with periodic boundary conditions. What if we have a boundary, not a periodic boundary? What are the allowed boundary conditions, and how can we study them? This is on my agenda to do. Some of the models in the literature, people studied it in the lattice, so there's something to relate to. I believe it's going to be completely straightforward because the field theories are free. After all, these are free field theories. Right. So whatever, there's some Neumann, Dirichlet, whatever, you need to put some condition on the boundary. You could ask, what are the allowed conditions? You don't want to mess the structure of singularities, of how to deal with the singularities that I mentioned before. And we should also get our guidance from the lattice literature, how to deal with that. So I think that this can be a very interesting thing to work out. What are the allowed boundary conditions? How can they affect the answer? What is the spectrum of the theory when we put it in finite space, not with periodic boundary conditions, but in some other boundary condition, with some other boundary condition.
Very interesting. Thanks. Other questions, comments?
I have a very naive question. Is
Go
it
ahead.
is it meaningful to ask about hydrodynamics of such models, like some diffusion, some analog of a diffusion equation here?
Well, personally, I think that whatever is usually done in quantum field theory should be redone. Whatever question you normally use in quantum field theory, you should be able to ask the same question here. And the formalism is not that different than standard quantum field theory. We spelled out the differences. And I think we should go through all the things that are normally being done, including hydrodynamics, boundary conditions, as in the previous question. And a lot of the stuff will be completely straightforward, and other aspects will need new thought. There's enormous, well, what we have done here is to enlarge a little bit the kind of quantum field theory that one should be interested in. And then there's a lot of things that can be done with it. And some of the results will be interesting and others will not be interesting.
Yeah, I asked because you said that there is some, in the first model, you had a dipole charge which don't allow charges to move in the first place.
Yes.
So in that sense, the diffusion equation should not even exist
Well, we can take derivatives and we should ask, well, first of all, there are many models, so we should study all of them. And we can write equations where we have fields, we have equations, and we have to make sure that we respect these rules of the singularities. And the rules of the singularities is something about the derivatives, how the derivatives act. And it might be that the standard diffusion equation does not work, but there's a diffusion equation prime that does work. The derivatives are a little bit different. Just as the gauge theory here is not the standard one, but slightly different.
So you're saying
I'm not giving you a satisfactory answer. In fact, I'm telling you that this is an interesting thing to explore.
So you are saying that just like in non-commutative field theories, we have to define derivatives in a new way in order to take higher order interactions. Maybe you have to do something similar.
Yep. In fact, this thing is very reminiscent of non-commutative field theories in many ways. It has this UVIR mixing, has higher derivative terms, it does not have the rotation symmetry. And various things need to be rethought, and they're a little bit different than in ordinary field theory, but they're not that different.
Thanks.
Other questions, comments? Okay. If there's no more questions, let's unmute ourselves and thank Nati again. And maybe we could move on to the next speaker. Zohar, would you like to share your screen?
Can you see that now?
Yes.
Should I start or should I wait until 11:10? Sorry, I guess 8:40.
It's just 2 minutes away, so I guess we could start. So we're happy to have Zohar Komargodski as a next speaker. He's talking about the high temperature limit of QFT. Go ahead, Zohar.
Thank you so much. Yes, I'm very happy to be here, and it's a very interesting occasion, and all the talks that I attended so far were very inspiring. So thanks again. So my talk is based on a paper from the end of the spring with the group at the Hebrew University and my students Chang-Ha Choi, and also some ongoing work. Some of you may have heard an earlier version. I gave 1 or 2 talks about it in the summer. But I'll also say some things that are new, which are based on some ongoing work. And also, I think, like Nari said, since I'll stop for questions once in a while, but since it's not such a huge group, please feel free to interrupt me at any moment with any question, pressing or not. So I'll start with a little bit of introduction to what is the question that we're trying to ask. So we know from many, many different examples that many quantum systems break spontaneously some symmetry at zero temperature or at low temperatures. So we know the example, well, probably the most famous example is just magnetism, which corresponds to a breaking of the rotational symmetry. Then more sophisticated examples are, for instance, QCD in the chiral limit, which breaks a chiral symmetry. In condensed matter, there is the nail phase, in which the spins order in a funny way. And of course, there are many, many other examples of symmetry breaking. Now, the usual intuition is that if we heat these systems up, namely if we just raise the temperature sufficiently, then at some point all the symmetries are restored. So there should be some beta below which, for any beta below that critical beta, all the symmetries are restored. Now, I'm talking here about ordinary symmetries, such as chiral symmetries, the spin rotation symmetries in magnets, and so on and so forth. I'm not talking about I'm not going to talk much about higher symmetries, but I'll mention something at the end concerning higher symmetries. Okay, so this is a standard intuition. And indeed, if you look at experiments, this has a very concrete, a concrete reflection in the phase diagrams of materials. So for instance, consider, by the way, you see my mouse when I'm moving it, right? My cursor.
Yes.
Yeah, so thanks. So the reflection of this fact for phase diagrams is, of course, that there can be a zero temperature fixed point. So for instance, in this model, there is a zero temperature conformal filter, and then there are phases on the two sides at zero temperature. But when you heat the system up, the black line goes to the left, meaning it caps off the ferromagnetic phase. So the phase that disappears if you heat up the system is the ferromagnetic phase, not the paramagnetic phase. So the fact that symmetries are restored at high temperature just means that if you start from a critical point, a phase transition point at zero temperature, the phase transition line goes one way or not the other way. And it's kind of funny that, I mean, one can ask, is it really a theorem that it always has to go to the symmetry broken phase? Now, why do we think that this is correct? First of all, of course, there are all these experiments. In all the experiments that I am aware of, it's always true that at sufficiently high temperatures, some symmetries are restored. On the lattice, it's easy to prove. But it might even be true in quantum field theory, which is the topic of this talk. So one piece of intuition is that at finite temperature, we do not minimize the energy, we rather minimize the free energy. And at sufficiently high temperature, that's tantamount to maximizing the entropy. And usually we think that in ordered states, namely symmetry breaking states, the entropy is not maximized. You can maximize the entropy by making the spins wiggle in all possible directions. So the symmetry should be restored. That's what we're taught in school. That's why magnets are supposed to lose their magnetism at high temperatures. Now there is a much more highbrow reason, which is actually the motivation for why I started working on this subject, is that this statement of symmetry restoration at high temperature is dual to the no hair theorem for black holes. So we know, I'll actually say a little bit more about it soon, but we know from the ADS-CS CFT literature that at sufficiently high temperatures, the gravitational ensemble that best describes field theory is the Reisner-Nordstrom black hole, which doesn't have hair if it's sufficiently hot. So at high enough temperatures, the ADS-CMT community essentially proved some sort of no-go theorem, which has lots of loopholes, but you know, they studied the instabilities of large Reisner-Nordstrom black holes, and they proved that there is no hair to the extent, you know, that their assumptions apply. So the no hair theorem is basically dual to the statement that there is no symmetry breaking at high temperatures in a conformal field theory. So the question that I want to pose is very clear. There you take a conformal field theory, a zero temperature conformal field theory. You heat it up. Now, since it's a conformal field theory, it doesn't matter what the temperature is. There is no other scale in a conformal field theory other than the temperature. If you don't have chemical potentials and stuff like that. So I'm assuming, let's just turn on a temperature without any other scales, then any temperature is the same as any other temperature. And you can ask, can symmetry breaking take place as soon as you turn on a non-zero temperature in some conformal field theory? So if the answer was that yes, symmetry breaking can take place, that would mean that there are like phase diagrams of that nature, that you have some conformal field theory, which could be a zero temperature phase transition, but then the disordered phase is capped rather than the ordered phase, which can continue to arbitrarily high temperatures, which, as I said, would be somewhat bizarre. And we've never seen such phase diagrams. Let me also make a little comment for the ADS-CFT or ADS-CMT experts in the audience. You can also add the chemical potential for the said symmetry. It could be a U1 symmetry, it could be a Z2 symmetry. So there, the picture that emerges from experiments in superfluidity or the ADS-CFT correspondence is that at temperatures below the chemical potential, you have symmetry breaking. So the system is described by a superfluid plus fluid. There is a broken symmetry at low temperatures, and that's described in ADS-CFT by a hairy black hole. However, at high temperatures, the hair disappears. This is something that Gapser found. This instability to developing hair was found explicitly by Gapser like 12 years ago. So at high temperatures, the instability disappears, the superfluid disappears, and you have a fluid. So the symmetry is restored. And that's basically the no-hair theorem that I referred to, that at sufficiently high temperatures, there is no known instability for the rise Nordstrom black hole. Okay, so the question is, and of course, the superfluid helium transition is exactly of that sort. It happens at very low temperatures, as you know, but that's exactly the same thing. So except that there we use pressure, perhaps, but it doesn't matter. It's the same type of thing. So the question is if it's really true. So I just motivated the question by saying that experiments, the no-hair theorem, and also thermodynamic arguments, common sense arguments, all suggest that at high enough temperatures, the expectation values of all the order parameters vanish at infinite volume. And the question is if this is really true, that no order parameter can get a VEV at high temperatures. Are there any questions about the introduction, motivation, any objections? Okay, I'll continue. So just one additional piece of historic reference that is curious is that Weinberg constructed in '74 a model with intermediate symmetry breaking. So that model was not a conformal field theory, and there was another scale. But so what Weinberg achieved is that he found a model where at some intermediate temperatures, not asymptotically high temperatures, there is some symmetry breaking. However, there is no symmetry breaking at zero temperature. That's already surprising. And this model led to a lot of follow-up work. But just to emphasize, in Weinberg's model, it is not true that at high temperatures, the symmetry is broken. It's an intermediate temperature story. There are also many materials in nature that exhibit this kind of intermediate temperature symmetry breaking phases. For instance, this particular salt, it has a crystal structure in some range, which is like room temperature range, which is a higher crystal structure than the low temperature phase. But of course, if you heat it up, this crystal melts and it becomes completely disordered. So here the question, so since I want to make contact with the no-hair theorem eventually, the question here is really about CFTs. I want to start with a CFT, heat it up, and ask if we can have symmetry breaking. So it's really a question about the ultimate high temperature limit of QFT, because you can think about the high temperature limit of arbitrary QFT as the non-zero temperature limit of the UV CFT. So it's really the same. So just to pose the question very precisely and tell you what I'm going to present. So the question is, are there unitary, local, non-trivial conformal field theories? And I'm also adding this this condition that they should have a finite number of fields or degrees of freedom. That just because I think that maybe examples with infinitely many degrees of freedom are not strictly going to be, experimentally interesting. So are there unitary local non-trivial CFTs which break a global symmetry at finite temperature? Okay, that's a question. I believe the answer to this question is not known. There is neither a theorem that this is impossible, nor is there a counterexample. But the reason that I'm giving this talk is that we've found a class of examples in fractional dimensions, namely Wilson-Fisher fixed points. So we found a class of examples in 4 minus epsilon dimensions. These examples are of the Wilson-Fisher type, as you will see. They're just a little bit more sophisticated. They work in some range of epsilon, which we do not actually know yet, but it's definitely a non-zero range around 4 dimensions. It's definitely true in 3.99 we checked, but we don't know how far it goes. This is a question that is somewhat, that's definitely solvable, but we haven't done it yet. And so we found these conformal field theories, which do exhibit actually symmetry breaking at finite temperature. So we have a counterexample, but it's not quite legit because this is a fractional dimension conformal field theory, and fractional dimension conformal field theories are not, strictly speaking, unitary. If you actually look at the conformal block decomposition of correlation functions of conformal field theories in fractional dimensions, and you go to high enough dimension, you do encounter some negative norm states. So it's not, Wilson-Fisher fixed points are not, strictly speaking, unitary in fractional dimensions. So for this reason, this is not a full-fledged counterexample yet. However, these conformal field theories are still interesting, and many things I will say carry to, strictly speaking, 3 dimensions. So there will be still some things I can say about it. Now, how you could attack this problem by trying to prove a theorem, or you can try to just look at examples. Weakly coupled conformal field theory is experiments and maybe some complete, the bottom-up ADS constructions. There was some work on that recently also. I'll mention it soon. And also, I'll show you that some theorems can be proven weaker than what we want, but they still can be proven nonetheless. Let me just make 2 final comments, which are, 2 final sort of general comments before I get into some more detailed discussion. So finite temperature field theory is essentially the same as a lower, reduces to a lower dimensional field theory below the scale of the gap. So for that reason, if you're doing a 1 + 1 dimensional field theory, while in 0 temperature, 1 + 1 dimensional field theories can definitely break a Z2. That happens in the Ising model in 2D. There is no possibility for symmetry breaking at finite temperature in 1 + 1 dimensions, any discrete or continuous. And that can be shown explicitly from modular invariants of 1 + 1 dimensional conformal field theories. Or you can think about it a little bit more conceptually by saying that at finite temperature, it's quantum mechanics. And in quantum mechanics, there is no notion of symmetry breaking since there is no large volume limit. In 2 + 1 dimensions, for the very same reason, there is no possibility for breaking a continuous symmetry at finite temperature. You can break a continuous symmetry at 0 temperature, but not at finite temperature, because at finite temperature, it's forbidden by the Coleman theorem. So in 2 + 1 dimensions, you can still hope to break a discrete symmetry. So you can have discrete hair in ADS4, or you can have continuous hair in ADS5 at high temperature, but you cannot have continuous hair in a 3-dimensional field theory at finite temperature. Instead, typically, if you look at a superfluid helium in 2 + 1 dimensions, typically you get a BKT transition rather than a symmetry restoration or symmetry breaking transition. All right, so this ends the introduction, and I want to just review some facts about thermal field theory that are important to bear in mind when we will discuss our main examples. So I'll just remind you some facts that you are probably all familiar with, and I'll do it quickly. So if you start from the 5⁴ model in 3 + 1 dimensions, we all know that at long distances, it's solvable because 5⁴ becomes a weak. The coupling constant lambda goes to 0 slowly, but it does go to 0 eventually. and the model is therefore completely solvable at long distances. But if you put this model at finite temperature, you may encounter some trouble. So let's indeed put the model on a circle of radius beta and expand it in modes. So you should concentrate on these pieces, which come from the zero modes on the circle. These are some interactions between the zero mode and higher modes. So now you're doing a 2 plus 1 dimensional field theory, since you've reduced the model in a circle. And in the 2 plus 1 dimensional field theory, the quartic interaction is actually growing strong. So now you might face some difficulties because you might be driven to a non-perturbative regime where you don't know what to do. So even though the original model was easy, it may not be true that at finite temperature you can solve the model. So in this particular case, you're sort of saved from strong coupling because these interactions generate a mass for the zero mode. So these interactions generate a mass for the zero mode phi naught, just because you need to put the higher oscillators phi n in their ground state, and that generates a positive mass. So you can compute it by just computing these diagrams. It's in every textbook, and you get a mass. Now, there is a miracle here, and this miracle is the sign of what's going to come, that this mass chord is actually positive. And it's related to the fact that this sum that we know from the Casimir energy in 2D is negative. So there is some conspiracy of signs, and eventually the thermal mass that is induced for the zero mode comes out positive. And it is for this reason that when you heat up the model, the ferromagnetism disappears. So you get a paramagnetic phase. So the no-hair theorem, or this statement that at high temperatures the symmetries are restored, is really a statement about some funny sign that comes up in some loop diagrams. But it seems robust. Like in every example that you look at, it seems that in the end of the day, the sign comes up in the same way. So this sign is really just the direction of this curve that I showed you before. So the sign controls whether it goes this way or that way, and it's very crucial which way it goes, of course. All right. So what I wanted to say here is that now I'm going to present some examples which do not do this, which behave differently. They're going to be in fractional dimensions. They're going to be conformal field theories of the Wilson-Fisher type. So, but when I present these examples, you have to keep in mind that this subtlety is taken care of. Namely, while the models are easy at zero temperature, they're just Wilson-Fisher fixed points. At finite temperature, this difficulty arises, and we have to compute the thermal mass and make sure that everything is weakly coupled, so we do not run into strong coupling dynamics. Okay, so let me just list the possible sort of models you can hope to study in order to address this question. So what I'll do today, since I have very limited time, I'll just talk about vector models, Wilson-Fisher models in the epsilon expansion. I'll just show you what we can say about those models. Then there is some work on weakly coupled conformal gauge theories of the Bank-Zaks type. I'll make some comments about it at the end. I'll tell you whether what is the status of those examples. Then there are also 2 plus 1 dimensional fixed points of the Chern-Simons matter type. I'll tell you what we know about them at the end as well. And again, I will not talk about ADS constructions, but you can look up some very nice work recently by Alex Bushel, who tried to challenge this no-hair theorem, saying that Reisner and Nordstrom black holes, which are sufficiently big, do not have instabilities. As far as I know, he actually did not find counterexamples, but he constructed some very interesting things nonetheless. And at the end of also I have like 25 slides at the end about the thermal bootstrap approach to try to understand this no-hair theorem, which I can talk about, but that would require much more time, I assume. Okay, so before I plunge to a detailed discussion of what we know about Wilson-Fisher fixed points as far as this problem is concerned, are there any questions? Just wait for 10 seconds. Okay. So the setup is very simple. It's very elementary. We have n scalar fields with some arbitrary interactions an arbitrary symmetric tensor in 4 minus epsilon dimensions. And I'll first study these models in the small epsilon limit. So the smallest parameter is epsilon. Of course, this is a very well-known setup. We know how to look for fixed points, and then I'll tell you how to study their finite temperature properties. So we have to look at, since epsilon is taken to be the smallest parameter, you have to solve for the beta function equations. And the beta function equations, after some rescaling and reshuffling, reduce to these equations. So these are some complicated equations for tensors with 4 indices. And actually, nobody classified the solutions, even for small n, where n is the number of fields. So n is the number of entries, of possible entries of each index. Nobody, like for sufficiently high n, like 4 or 5, I think nobody classified the solutions. But of course, with, during like the 40 years or 50 years since Wilson Fisher, people have constructed many classes of solutions. So we know many, many examples of solutions, but nobody constructed the most general solution yet. Now, another thing you can do before you start studying the solutions is that you can ask what happens when you turn on a finite temperature. That's an easy question. You just need to do it. You basically need to compute these diagrams, but in these more complicated models, and you have to take into account that you're in 4 minus epsilon dimensions. So what you find out is that the thermal mass matrix is given just by a trace of this coupling constants, lambda I, j, k, l, but you have to trace 2 indices, so kk. So you have a very explicit expression for the thermal mass, and you can also try to use the beta function equations, namely this relation, which is a nonlinear equation for these 4 index matrices, to give a formula for the thermal mass. And very nicely, the first piece is manifestly positive. So this is a manifestly positive object. No, sorry. Sorry, I meant to say this is a manifestly positive object. And the first piece is not manifestly positive. So a priori, there could be examples where the thermal mass that's generated is negative. And if the thermal mass that is generated is negative, it could well be that there is symmetry breaking. So let's quickly go over the simplest example, which is in every textbook. You can read about it in Sachdev's nice textbook on condensed matter physics. The simplest example is, of course, the ON model. That's the model that is known best. It's the simplest solution of the beta function equations because ON symmetry restricts this tensor to take this form. Alpha is some coefficient that you gotta determine from this equation. It's straightforward. You determine it, and you find that it's equal to 1 over n plus 8. And you compute the thermal mass, and you find that it's positive. That's it. So at this conformal field theory, the thermal mass is positive, and that means that when you heat it up a little bit, you are in a paramagnetic phase. There is no symmetry breaking. And this is why magnets behave like we know. That explains a lot of experiments in phenomenology. This is the ON model. But it turns out that that there is more to say. First of all, there is a huge class of models that is different from the ON models. Let's suppose that we try to preserve a group G, which is a subgroup of the ON model. Many of these models are also interesting experimentally. So first, I can quote, but not prove because it will take too much time, a no-go theorem. So let me just quote the no-go theorem. The no-go theorem essentially says that if G is big enough, there is no symmetry breaking at finite temperature. What does big enough mean? Big enough means that the fundamental representation of ON is irreducible as a representation of G. That's what it means for it to be big enough. If the fundamental representation of ON is irreducible as a representation of G, we were able to prove, it's in the paper, that no symmetry breaking takes place. But there are many models which are not of this type. There are many models which are interesting experimentally, where G is not big enough. So for instance, we have the MN models, the bifundamental models, the trigonal models, Michel fixed points. Sorry, I misspoke. Those are models that do obey the condition that G is big enough, but there are many models that do not obey this condition, and I'll talk about them soon. So the no-go theorem covers a large class of examples, including all this list of models, and you can where G is big enough, but there are many examples where G is not big enough, and I'll talk about one of them and mention others. So let's start with the simplest example where G is not big enough, namely the fundamental representation is reducible. And this is just a class of fixed points which are called the biconical fixed points. I do not know why they're called the biconical fixed points. It's probably some historical thing. But the crux of the matter is that they have this symmetry group, OM times ON minus M. And clearly the fundamental representation, this is embedded in the obvious way into ON. And so clearly the fundamental representation now reduces to the fundamental representation of OM plus the fundamental representation of ON minus M. And hence the fundamental representation is reducible. And so these models do not fall into the no-go theorem, and one has to separately analyze them. Okay, I'll just quickly go over the analysis. The bottom line is going to be that these biconical fixed points do admit, so let me just tell you the bottom line for those that will not follow the details. The bottom line of this analysis will be that as long as M and N minus M are not the same, one of those groups will be broken. So in the case of equal rank, accidentally there is no symmetry breaking. But as long as if the rank is different, the smaller group is spontaneously broken at finite temperature. So this is the simplest class of models where we found that all this intuition from thermodynamics and ADS-CFT is not obeyed. In these models there is symmetry breaking at finite temperature. Now let me just walk you through how this is found, how this is derived. So first you write down the most general potential that's consistent with these symmetries. So you have three coupling constants, alpha, beta, and gamma, and these are the exact beta function equations in the limit of very small epsilon. So these are some quadratic equations. You cannot solve them analytically, but you can of course just find numerical solutions. It's straightforward. So let me just make a comment about the equal rank case. I already told you that in the equal rank case, it will turn out that there is no symmetry breaking. And the equal rank case is actually analytically solvable. You find that, and you can also compute the thermal masses. And they're positive, so there is no symmetry breaking. But now you want to understand the non-equal rank case. And so to understand the non-equal rank case, you can just put these silly equations on the computer, look for solutions, compute the thermal masses, minimize the potential, and exhibit symmetry breaking. You don't have to do anything sophisticated. It's just an easy exercise in Mathematica to do it. But because it's a little bit peculiar, I want to show you an analytic approach of how to solve this model. So you take a large n limit. We're still in the regime where epsilon is the smallest parameter, but we also take n to be somewhat large, just to simplify these quadratic equations. This model exhibits then some peculiar properties that hold all the way to epsilon equals 1. So I just wanted to tell you about it. In this large n limit, there is actually a whole circle of fixed points. It's not true that at finite n there is a circle of fixed points. At finite n there are maybe isolated fixed points, but at infinite n there is a whole circle of fixed points. So there is an exactly marginal operator. And many of the points on the circle you can easily recognize. One of them is just the critical ON minus M model. Another is the critical OM model. Another one is where there is an enhanced ON symmetry. So the coupling, so you see that in this Lagrangian, there is an obvious solution where alpha and beta and gamma are all the same. Then you can combine it into a square and you get a full enhanced ON symmetry. So you recognize many points on the circle, but all the rest are not easily recognizable. And mostly there are just artifacts of large n. Only maybe a few additional points survive at finite n. So one fact is that at large n you have the circle. Another fact is that many of these fixed points that you find at large n, they have a flat direction. And this flat direction exists at 0 temperature. But surprisingly, even at finite temperature, this flat direction remains, except that the flat direction is deformed. This is a very, like you might remember, Seiberg's deformed moduli space from supersymmetry. This is like a silly example of that without supersymmetry. We have a model with a flat direction at large n. Then you heat it up, and you might expect that the flat direction would disappear, but instead it's deformed. It's deformed this picture is silly because it's in the phi 1 squared, phi 2 squared plane. It should have been a straight line. It's a hyperbola in phi1, phi2. That's what I meant to draw. So it's deformed from a straight line to a hyperbola in phi1, phi2. And because this moduli space of vacua is deformed and the origin is no longer a part of the moduli space of vacua, it's obvious that symmetry breaking takes place because it doesn't matter where the true vacuum is. Every point on this flat direction breaks some symmetry, which is again a little similar to the deformed moduli space in the supersymmetric theories where either baryon symmetry or some mesonic symmetry is broken. So the whole story at large n boils down to understanding if the potential is deformed in this way or if it's deformed in this way. That's all there is to it. You got to compute this coefficient C, which tells you in which way the potential is deformed if you want to understand which symmetry breaking takes place. So the answer is the following. If you take equal rank, it's not deformed. If you take non-equal rank, it's deformed in one of those two ways. And you got to compute the sign, and it's an easy computation, which we've done. And the conclusion is the following. I'm just jumping through all the details. I'll tell you the conclusion right away. This is the conclusion. If M is bigger, X is the ratio of M and N, as I introduced before. Let me just remind you what X was. X was the ratio of the two ranks. So if one group is bigger than the other group, let's say M is bigger than N minus M, then this is the true vacuum. So it's at the apex of the hyperbola. And if vertex of the hyperbola, sorry, not apex, the vertex of the hyperbola. And if M is smaller than N minus M, the hyperbola changes its shape from being like that to like that. And you're again at the vertex, correct vacuum is at the vertex of the hyperbola. What does it mean? It means something very simple that you can just remember. You don't need to know any of these details. So if for this symmetry group, it's the smaller group of the two that is spontaneously broken. And if the rank is equal, none of them is broken because there is no smaller one. So if you just take like a large n limit, that means that at finite temperature, X equals half has a thermal gap. That's the case of equal rank. But all the other X's, namely all the cases where the rank is not equal, there are Nambu-Goldstones, namely superfluid. It's like a non-abelian superfluid type of thing. There are Nambu-Goldstone bosons at any temperature, and they're never lifted. Are there any questions about the conclusion? I jumped through a lot of the derivation, but hopefully the statement is clear.
Zohar, you're working always at small epsilon. Presumably at large n, you could work at any epsilon.
That's right. That's yeah, that's one question. I'll just write it for myself to respond. Yes. Yes.
And when you go to epsilon equals 1, you explained to us that none of the symmetry breaking can happen. Is that correct?
Yeah, I'll respond to both questions now. Thank you, Shiraz. Both questions are hopefully explained somewhere in the slides, but since I'm not being very systematic in covering, I may have forgotten to say. So first of all, these conclusions about the existence of a moduli space of vacua, a deformed moduli space of vacua, they're true for any epsilon at large n. The crucial question is, which fixed points remain at finite n? Because you want at least one fixed point in this, which is not the blue points or the red point. The red star and the blue points are trivial. We've already analyzed them before. These are just the critical ON model, which does not exhibit any symmetry breaking at finite temperature. So you need some fixed points to survive in some new region, all right? And this we've shown at a sufficiently small finite epsilon and large n, or finite n, sufficiently small epsilon. So we have shown conclusively that this phenomenon happens for either finite n and small epsilon, or a finite epsilon and large finite n. However, we don't know how large epsilon can be. We did not do an exact resummation in epsilon. So we just know that this is true for some sufficiently small epsilon. I meant there is a point in my later slides where I will say this exact thing that I just said now. I just don't know if I can find it right away. But we do not know up to which epsilon you can go for these statements to hold true. One thing you can say for sure is that at epsilon equals 1, this doesn't make sense, because at epsilon equals 1, you cannot have finite temperature continuous symmetry breaking. I'll say much more about it actually soon. Okay, so is the statement clear, Shiraz? What's the regime where we can establish these results?
Right. So even if you're at large n, you say that this picture holds for some range of epsilon, but stops before epsilon equals 1.
I don't know if it stops before or not. I know that it definitely does not proceed to strictly 1, but I don't know if you can go, if it's an open set all the way to 1. This requires a certain resummation of epsilon corrections that is certainly doable, because you can take large n first. But you need to do some 1/n expansion that we have not done for arbitrary epsilon yet.
Thank you.
But I mean, the reason that I'm giving this talk is that we do have concrete examples, which are finite rank, finite epsilon, where this works. This is definitely true.
Yes,
So there are field theories that exhibit this phenomenon at finite rank and finite epsilon. Yeah, oh, exactly, that's what Shiraz asked. So these conclusions hold for small finite epsilon, but I don't actually know up to where. This is a computation that we're hoping to do in the future, or if somebody maybe beats us to it. Okay, so this is the symmetry breaking pattern at finite temperature in this regime that I spoke about. And clearly, this cannot be literally true at epsilon equals 1, because we cannot have continuous symmetry breaking at finite temperature. Yet it's still very interesting if it's true in epsilon equals 1, because the Coleman theorem just means that the Nambu-Goldstone bosons wouldn't survive, they will be confined. But this has a tiny, tiny scale associated to it, which is exponentially small. So it's still interesting. It would be not strict symmetry breaking at finite temperature, but it would be a case where the thermal gap is much, much, much smaller than the temperature. That's still interesting in 2+1 dimensions. Okay, let me just make one comment about the case of m equals 1. I wanna make some comment about m equals 1. M equals 1 is a very interesting case, because for m equals 1, this symmetry breaking is not continuous. It's actually discrete, because O1 is Z2. And this can actually occur, strictly speaking, already in 2+1 dimensions. You take large n, you study the Ising model coupled to the ON bath, and you ask if this system can exhibit symmetry breaking. And that's something that I spent like a month of my life trying to understand. And the way it turned out is very interesting. So what happened is that we try to understand the Ising model coupled to an ON bath motivated by this epsilon expansion results strictly in 2+1 dimensions to try to understand if there is a conformal field theory that you can control and show that it breaks the symmetry at finite temperature. So this can be studied using conformal perturbation theory, because the Ising model is not, we cannot solve it exactly in 3D, but we have a lot of data from the conformal bootstrap. And we also have a lot of data about the ON model. So you turn the crank, you can do a very detailed conformal perturbation theory computation. And the whole question ends up depending on the sign of this OP coefficient in the standard ON model. So it's the energy OP coefficient in the standard ON model in 2+1 dimensions at large n. And at the time, we didn't know this coefficient. We know that it vanishes at order 1/√n. That is known from higher spin symmetry from Shiraz and collaborators and Maldacena-Zhiboyedov, and I think it's even before. It must have been due to Itzikson-Zuber. They already knew that this OP coefficient vanishes at order 1/√n. And so we really needed the next order to understand if this phenomenon takes place or not. And then there was a heroic computation just a few months ago by Goichman and Smolkin, who computed for the first time this OP coefficient at this order, and they found that it vanishes. So this was really a big blow, because now we don't know. So very strangely, since this OP coefficient vanishes for some unknown reasons in 3D, I don't know if this example persists to epsilon equals 1. So I do not know if this persists all the way to epsilon equals 1 when m is equal to 1. That's very unfortunate, but it's a sign that maybe there is a theorem, because it's really evaded the theorem in a very sneaky way. Now, the vanishing of this OP coefficient is by itself a very interesting fact, because the same OP coefficient vanishes in 2D due to Kramer's Vanier duality. And here we see that it vanishes all the way to this order for some mysterious reasons. Another conspiracy that seems to be going on is that there is an upcoming paper by Choi, Rabinovich, and Sumyadip, where they've basically scanned very systematically a huge amount of quiver gauge theories in 4 dimensions, which have Banks-Zaks-like fixed points. And they've asked if some continuous symmetries can break at finite temperature in these fixed points. And in many examples, it was a priori possible, and we even thought that we found examples at some point. But when dust settles, they all evaded somehow at the end of the day. So they have not been able, as far as I know, to find any examples strictly in 4D at finite rank. And that's another sign that something is going on. One more comment that I want to make is that this problem of symmetry restoration at high temperature is very closely related to the problem of deconfinement that at high temperatures, which is something that David Gross and collaborators pioneered. They have shown in the days that gauge theories are deconfined at high temperatures by doing an explicit computation for the potential of the holonomy. Actually, in 3 dimensions, not in 4, but just in 3 dimensions, these problems are dual. So a Z2 symmetry restoration at high temperatures is dual to a Z2 deconfinement at high temperatures. This is just because if you gauge an ordinary Z2 symmetry in 3 dimensions, you get a bonus quantum Z2 one-form symmetry in the dual model. So the no-Harry theorem is really equivalent, at least in 2 + 1 dimensions, to high temperature deconfinement. So this problem, if you can solve this problem that I'm posing, it also proves deconfinement in 2 + 1 dimensions at high temperatures, which is interesting. So what did we learn? How am I doing with time? I'm confused. Okay.
Yeah, you're almost done, but you could take, how much more time would you like?
I just need 2 minutes.
Yeah, go ahead, please.
So what did we learn? I told you that it seems that it's not impossible that a critical point, namely a CFT, would be in a broken phase at finite temperature. That violates thermodynamics. It violates the no-Harry theorem. It violates our common sense, but it's possible. I don't yet have constructions which are strictly speaking in 3 + 1 dimensions or 2 + 1 dimensions. And in fact, I've come to believe that they don't exist, since every example that I looked at eventually mysteriously evaded this conclusion. So that means that there may be a theorem, there may be a proof, and I don't know. This is something to be studied. I would like to thank you at this point. As I said, I have 20 more slides about the thermodynamic implications of symmetry breaking at high temperatures, but it doesn't lead to a proof yet. It only leads to some peculiar things that you can infer. So I'm happy to stop here. Thank you.
Okay, let's unmute ourselves and thank Zohar for this nice talk. Very interesting. Questions and comments?
Could I ask a question?
Yeah, Shiraz, go ahead. Yeah.
Somewhere in your slides, somewhere in your talk, Zohar, you mentioned that it was possible that you would have something that broke symmetry in the strict large N limit, but at epsilon = 1, and that this symmetry breaking then goes away when you turn on finite N effects in an exponential.
Yes.
Do you have an example of that phenomenon?
Yes, definitely. For instance, this circle of fixed points exists also at epsilon = 1 in the strict infinite N limit. When you turn on, and many of the points on the circle of fixed points, if you stay within the infinite N limit, exhibit symmetry breaking at finite temperature. However, if you turn on finite N corrections, there are small corrections to the beta functions, and actually this whole circle is basically lifted. So all of the candidate fixed points that did the job disappear.
And sorry, can you remind me, if you just take the ordinary ON, the model that preserves the full ON symmetry?
Yes.
And then we turn on a mass and a temperature.
Yes.
Is there any finite temperature phase there, strict large N, in which the symmetry is broken?
Oh yeah, if you take the mass to be negative, mass squared to be negative, you're in the superfluid phase. Then you heat it up and you cross over to the paramagnetic phase.
Yes, but at finite, even at finite temperature, the broken phase survives. Is
Yeah.
there a,
Yes. If you are in a broken phase at 0 temperature, it must survive small temperature corrections. There is no mechanism by which. Let me think about it for a second. Yeah, if you have an infrared free theory of Goldstone bosons, you put it on a very large circle, way below the cutoff of the nonlinear sigma model, the Goldstone bosons are not going to disappear. Unless you're dealing with a situation of the Coleman-Mermin-Wagner theorem type. But as I said, they disappear at some exponentially smaller scale. But if you go from 3+1 to, you take a 3+1 dimensional model, or let's say 3.99 dimensional model, and reduce it on a circle, you are bound to still have Nambu-Goldstone bosons. So the broken phase cannot be eliminated by turning on a small temperature. Do you see what I'm saying?
I see what you're saying. There are, of course, lots of Goldstone bosons, order n Goldstone bosons.
That's right, but it's an infrared free model. You reduce it on a circle, you still get Goldstone bosons. They're not going to go away.
Okay.
But at finite temperature, which is high enough, they can disappear because at some point you hit the scale of the nonlinear sigma model, the cutoff scale. And then the KK modes become important. And
Sure. But I was just wondering. So right. I was just wondering if something funny happened even at a small temperature. You said
no,
that.
No, that cannot be.
Okay. Thank you.
Can I ask a question?
Yeah, go ahead, Rajesh.
Hi, Zohar. You mentioned in the beginning about perhaps the non-unitarity of these theories in 4 minus epsilon might be a kind of a caveat to this, might be a loophole through which this thing. But more specifically, I was wondering, in these 4 minus epsilon theories, there are all these evanescent operators which don't exist at the integer dimensions, but exist in the theory. So I was wondering whether, because the operator spectrum is perhaps so different in these fractional theories, could that potentially be a mechanism by which this is, by which you find this possibility in fractional dimensions, but perhaps it's not there in integer dimensions? I just want to hear your thoughts on it.
Yes, Rajesh, this is an excellent question. I do not know which exact thickness of these fractional dimension models is responsible for what I'm saying. The computation that we do for these models in 4 minus epsilon dimensions does not involve going to, it's a very basic computation, just a one loop computation of the thermal mass. Mm-hmm. And somehow secretly, it must be that some, thickness of these models creeps in, but I don't understand how. I don't know exactly if it's due to ghosts, namely negative mode operators, or it's due to evanescent operators. I do not know. I can tell you one thing which may be related, but I'm not sure, is that in integer dimensions, if you put an imaginary chemical potential that leads to oscillations in the partition function, it's known that there are ways to prevent a phase transition at high temperature with imaginary chemical potentials. The chemical potentials that I mentioned here at the beginning, about when I mentioned the superfluid story, the fluid superfluid story, when I meant, the chemical potentials that I spoke about here, they were real. And then we have this whole ADS-CMT literature and we understand. But when you put imaginary chemical potentials, I know of concrete examples which do not restore the symmetries at high temperature. So in those examples, it's clearly due to the oscillations of the partition function. And that suggests that maybe the fact that all the weights are positive is important.
Okay. Thanks. Yeah.
Other questions, comments? So Zohar, could you give us a preview of the slides you did not show, if there's no other questions?
Yeah, let me just stop the sharing.
Have you turned your slides off? I was wondering if you would show the slides that you did not that you were going to overview.
Oh, I thought you. I heard
No.
you.
There's still a few minutes, so I was wondering if you could just preview. I mean, just give an overview of,
it's like
or say something about it. Or whatever.
It's 20 slides. I'll send you all the slides, and people can look at them. But it's 20 slides. I won't be able to explain what is going on in those slides.
But maybe you could say something about it.
The bottom line of those slides is that I've presented the proof that there is some heat capacity which becomes negative if there is a symmetry breaking at high temperatures. But it's a certain heat capacity which is a little exotic. So there is no theorem that it's not allowed to be negative.
Is there any hint like this in any holographic description that you might have? Any gravity phase
I did
that
not,
you might have? Something?
Yeah, I did not mention that. So maybe I'll just, sorry. So there is a question of whether you can do a bottom-up holographic model which would exhibit an instability of the Reisner-Nordstrom black hole. That's an interesting question, and I believe the answer is probably yes, but I have not seen papers about it. There is another thing you can ask, which is whether there are top-down string models which may exhibit an instability of the Reisner-Nordstrom black hole. And Alex Bushel has surveyed in some of his recent papers many such things. And he found, what he found is that he did not find a counterexample, but he found examples where there were additional metastable phases which have a higher free energy than the Reisner-Nordstrom black hole. But what Alex found in the end of the day is that there are no counterexamples, at least not yet, for top-down string theories. For bottom-up string theory constructions, I believe there will be ways to destabilize the Reisner-Nordstrom black hole. For instance, you can just couple phi squared, which is the operator in the bulk, which is the hair, to the wild tensor squared, because the Reisner-Nordstrom black hole has a non-zero wild tensor, while flat ADS does not. You can just couple phi squared to W squared, or even just there are some other combinations you can use, and you might create hair even for large black holes. But these couplings may not be allowed in a top-down approach.
Right. Okay, maybe we should move on. Other question? Actually, we still have a few minutes, so let's just. This fractional dimension is a little reminiscent of some of these non-relativistic theories that have been studied, and I don't have anything specific to say, but.
No, it's just this fractional dimension is just the standard Wilson-Fisher.
I know from the field theory point of view, but I was just wondering if there's anything like that in any holographic setup that one could.
I don't know, but these are just vector models. What I talked about today are not H theories; these are vector models, and the ADS duals are typically some Vasiliev theories. Should I turn off my slides? I see no other questions.
Yeah, I don't see any other questions either. Okay, so maybe let's just let's unmute ourselves and thank Zohar again for a very interesting talk.
Thank you.
Maybe David could start sharing his screen.
Yeah. Hey. You want me to kick off now? This is the first conference I've ever been to where things are running on time. I'm very impressed with you.
I think it's a sessional thing. I think the session before was not necessarily that way, but it's whatever. I mean, it's yeah.
Let me see if this works. Okay, you see the screen?
Yes. And your pointer's fine. Yeah.
Good. You see the pointer on the screen. I can use that if need.
Yeah.
Good. You want me to wait for a couple of minutes or just kick off?
Maybe you could wait a minute or something, and then in case
whatever.
Other questions. Yeah. Okay, maybe we could just begin. So we are happy to have David Tong from Cambridge talking about chiral fermions. Go ahead, David.
Thank you. Thanks everyone for turning up. Thank you to the organizers for putting this meeting together. It's great to talk here. It'd be much better to talk actually in Chennai rather than here, but okay, this is the best we can do. I was reminded, seeing the names of lots of friends in the participants. I was actually in India in January. I had New Year in Mumbai with Shiraz. We were all wishing ourselves a very prosperous 2020. Turned out well, didn't it? I'm going to tell you about some simple comments, very simple comments on chiral fermions in gauge theories. And it's based on a paper that came out last month with Shlomo. And the whole talk is premised on an extremely simple question. And the question is just the following. Take a bunch of massless fermions, and for most of this talk, I'm going to be in 4 dimensions, 3 + 1. Take a bunch of massless fermions, and they have some symmetry, and give them a mass. And the question I want to ask is, what symmetry gets broken when I give them a mass, and what symmetry can possibly be preserved when I give them a mass? Okay, it's a very old question. It's a very simple question. Let me just give you a little bit of intuition for this. It's of course intuition that each of you already knows. Let me just take a single Dirac fermion in 3 + 1 dimensions and write down a bare mass term in the Lagrangian. So a quadratic mass term. The massless fermion, of course, has 2 U1 symmetries acting independently on the left and the right fermions. When I write down a mass, the vector symmetry, which acts in the same way on both fermions, is preserved. The axial symmetry, which acts oppositely on the 2 fermions, is broken by a mass term. A slightly more interesting way of giving a mass is not just to write it down, but to let the mass be dynamically generated. And again, something rather similar happens. If you take QCD with massless fermions, the fermions all get a mass, of course, but at the same time, a condensate is generated dynamically. It's the chiral condensate. And again, the symmetry which acts differently on the left and right moving fermions is then broken when the fermions get a mass. This time it's broken spontaneously rather than explicitly, but nonetheless, the chiral symmetry is broken. So these 2 examples might lead you to think that the story is when you give fermions a mass, it's the chiral symmetry that always gets broken. It's the symmetry which acts differently on the left and the right-handed fermions. And that's not quite true. And the fact that's not quite true was explained to us 40 years ago by Toft. So the correct statement is a little more subtle. The correct statement is that if you have a quantum field theory that has a global symmetry, which I'm going to call G in this talk, then associated to that global symmetry is a Toft anomaly. And if that anomaly is non-vanishing, then whatever you do to the theory, if you deform it, if you allow it to flow under RG, one of 2 things happens. This anomaly survives unless the symmetry is broken. So if the anomaly is non-vanishing, the 2 options are the symmetry G is broken either by explicitly adding mass terms or spontaneously if this happens under RG. Alternatively, if the symmetry is not broken, there have to be massless fermions left in the infrared which saturate the anomaly. And there are experts in the audience who know that actually there's a 3rd option, which is that the anomaly could be saturated by a topological quantum field theory. I'm going to ignore that option for the purposes of this talk. It's not going to play a role. So these are the two possibilities that we have. So what this means is that in the 2 examples I had before, it wasn't really the chirality of the symmetries, the axial symmetries, which was responsible for the fact that they were broken when the fermions got a mass. It was really the statement that their Toft anomaly was non-vanishing. That's why those symmetries had to be broken. And indeed, that was Toft's argument in QCD, that if QCD is to confine, the chiral symmetry has to be broken on consistency grounds. But this leaves open a new question. And the new question is, suppose you have a collection of fermions that have a chiral symmetry. So the chiral symmetry acts differently on the left and the right movers, but nonetheless, it acts in such a way that the Toft anomaly vanishes. In that case, is it possible that you give that collection of fermions a mass while preserving the symmetry G? That's the real question that I'd like to address in this talk. It should be clear that because it acts differently on left and right movers, you can't just write down a mass term in the action. So a quadratic term is not going to do it for you, but you might hope that there's some strong coupling dynamics that acts between all these fermions and allows them to become gapped, preserving the symmetry G. And as we proceed, it's useful to have a concrete example in mind. The example I want to run with is extremely familiar. It's just the standard model. So take the symmetry group SU3 times SU2 times U1 with a collection of fermions like the quarks and leptons in one generation of a standard model that have the famous quantum numbers that we all know and love. Famously, the anomalies vanish. The Toft anomaly vanishes. Toft anomaly has to vanish because, of course, in the standard model, G is gauged. And it's a prerequisite that the Toft anomaly vanishes in order to gauge a symmetry. So this is an example. You can think of G as global or gauged. It doesn't really matter. The question is it possible to give a mass to one generation of the standard model without breaking SU3 times SU2 times U1? And we'll see later in the talk, it is possible. Nature, of course, gives a mass to the quarks and leptons, but it does it by breaking SU2 times U1. There's a Higgs boson which couples to the fermions. The Higgs boson gives a mass, but at exactly the same time it breaks electroweak symmetry. So the question I want to ask is there an alternative? Is it possible to give a mass to one generation of the standard model without breaking electroweak symmetry? Okay, that's the motivation for where we're going. Are there any questions about the setup of the talk before I go on? I'll take that as a no. Let me tell you, before I jump in, a few examples where people have addressed questions similar to this in the literature in the past. So the first example I want to explain to you came out of condensed matter. That this was in large part the kind of thing that got me interested in these questions. And in particular, this idea of an SPT phase in condensed matter physics. SPT stands for symmetry protected topological phase or symmetry protected trivial phase, depending on your taste. So the idea is you have a bulk system, and the bulk is gapped while preserving some symmetry G. And what's subtle about the system, there's really nothing interesting going on in the bulk. The bulk is just boring physics. But what's interesting is what happens on the boundary. And the way the symmetry is realized necessitates new massless degrees of freedom on the boundary. Again, there's options for topological field theories that I will not discuss. But in the simplest cases, necessitates new massless degrees of freedom that live on the boundary. And those massless degrees of freedom carry the symmetry G, but also carry a Toft anomaly for that symmetry G. And there were questions about 10 years ago that were raised, which is when is it possible that the theory on the boundary, the fermions can actually become gapped? The reason people were asking this, and in particular, I have in mind the work of Witkowski and Kitaev from approximately 10 years ago, is that our condensed matter colleagues were realizing there were new subtle symmetries and subtle anomalies associated to symmetries that they didn't really understand what those anomalies were. And so they kind of inverted the question. They were asking, under what circumstances can a bunch of fermions be gapped while preserving a given symmetry, to try and get a handle on the anomalies that symmetry may have. Subsequently, we understood what those anomalies are, and the correct description is in terms of Bordism groups and so on. But when first asking this question, the gapping of fermions was a way to get a handle on the anomaly rather than vice versa. So the particular example that Witkowski and Kitaev did is really a beautiful calculation. I'll just sort of sketch what they did here. For the experts, I should also say this isn't quite what Witkowski and Kitaev did. This is actually the Witkowski-Kitaev calculation, but then with some different words that was draped around the calculation by Ryu and Zhang and by Xiaolang Qi a couple of years later. So the idea is the following. You take a bulk system, 2 + 1 dimensions, which is gapped, and gapped preserving a particular Z2 symmetry. And the boundary is now just 1 + 1 dimensions, massless fermions, Majorana fermions on the boundary. And the Z2 symmetry is realized on the Majorana fermions by chiral fermion parity. That means that it flips the sign of the left moving fermions, but leaves the right moving fermions completely untouched. Now, it should be clear, this chiral fermion parity prohibits writing down a mass term. Quadratic term in the Lagrangian coupling left and right moving fermions, necessarily odd under this. So if you want to preserve the symmetry, you're not allowed to just write down a mass term. But Fitkowski and Kitaev showed rather beautifully that it is possible to gap, given mass, to Majorana fermions, preserving this symmetry, provided that the number of Majorana fermions you have is a multiple of 8. And the way they do it is they write down a 4 fermion term. These are marginally relevant operators in 1+1 dimensions. These kind of 4 fermion terms were of course studied long ago by Gross and Neveu. But if you write down the usual Gross-Neveu 4 fermion term, you'll find the fermions get a mass, but in doing so, they spontaneously break this Z2 symmetry, which is protecting them. So the usual Gross-Neveu approach does not work to give fermions a mass preserving this symmetry. Instead, Fitkowski and Kitaev wrote down a rather pretty particular 4 fermion interaction that preserves an SO7 out of the SO8. They have a lovely argument that uses the triality of 8 Majorana fermions, linking it to Wess-Zumino-Witten models and so forth. And when they jump through a bunch of duality hoops, they're able to show that a particular 4 fermion term, and I'm not giving you the details, does indeed gap the system while preserving this Z2 symmetry. But again, it only works if the number of Majorana fermions is a multiple of 8. And in a more modern language, we understand what's going on here. We now understand that this Z2 symmetry has an anomaly associated to it. The anomaly is rather subtle, but it's a mod 8 anomaly. So there's a Z8 anomaly associated to this Z2 symmetry. The anomaly vanishes if you have 8 Majorana fermions, but it vanishes in a slightly trivial way because it's 8 and not 0. Okay, so that was the simplest case of what condensed matter physicists sometimes call symmetric mass generation. The idea you can give fermions a mass while preserving a symmetry that naively you think you shouldn't be allowed to preserve. For continuous symmetries, and in particular for the standard model, there's also a long literature describing this. And the literature is almost entirely in the context of lattice gauge theory. So the idea is the following. It's a long-standing and important problem to put chiral fermions on the lattice. And the difficulty, of course, is that if you discretize the Dirac equation, you don't only get the original chiral fermions, which sit at the origin of the Brillouin zone. So that this graph is an energy versus momentum graph for fermions. So you don't only get the original fermions that sit at the origin of the Brillouin zone. At the edge of the Brillouin zone, you get new low energy modes. Those new low energy modes have the opposite helicity, opposite chirality to the ones you start with. So you try to put a chiral theory on the lattice. Let's say you put all the fermions of the standard model sitting at the origin there. You'll find that you don't end up with a chiral theory. You end up with a vector-like theory with mirror images produced by the discretization of space that sit at the edge of the Brillouin zone. So one obvious way to try and realize the actual standard model is to take these fermions that sit at the edge. My pointer doesn't seem to be working. Let me point with my finger. I suppose it doesn't work for you guys. Let me take the fermions that sit at the edge of the Brillouin zone, try to introduce some interactions that only the ones at the edge, those ones circled in red, experience, so that the whole thing becomes massive. The doublers, the fermionic doublers, become massive while preserving the chiral symmetry of, say the standard model. That was the goal in the lattice literature. You may know there's something called the Nielsen-Ninomiya theorem, which guarantees the existence of these fermionic doublers. But the Nielsen-Ninomiya theorem relies on weak coupling physics. So if somehow you can include some strong coupling physics into the game, the Nielsen-Ninomiya theorem is not valid, and it is possible to lift these doublers. This is an old idea of Eichton and Preskill. It's been followed up by many people. I've listed several of the papers at the bottom of the screen. All of these papers have the following idea to gap the doublers. They want to write down 4 fermion interactions which give these objects a mass. Now, I think most of you in the audience are like me, quantum field theorists who are used to working in the continuum. And this just seems like a nonsense idea, because a 4 fermion interaction in 4 dimensions is an irrelevant operator. So it literally is irrelevant in the infrared. There's no way a 4 fermion interaction in continuum quantum field theory can possibly give fermions a mass. The idea here, though, is that you're working on the lattice. And if you're on the lattice, you can do things that you can't do in continuum field theory. In particular, you can take this 4 fermion interaction and you can crank up the coefficient so the interaction is strong at the lattice scale. So it's an interaction which is strong at the UV cutoff of the theory. At the UV cutoff, you don't have a continuum field theory, you have nothing like it, you have a discretized lattice theory. And it is possible in principle that by turning on such interactions, you could gap just the doublers, but leave the original fermions behind. Now, it's possible in principle, but in practice, it turns out to be much harder than certainly Eichten and Preskill were hoping. This has been explored in a number of papers. Every paper that's really looked at it in detail just finds that the idea doesn't work. And I suspect it doesn't work for annoying technical reasons, but the technical reasons are all to do with the fact that you're turning on strong coupling physics at the lattice scale. So you don't have any analytic control over this strong coupling physics at the lattice scale. It's complicated. But also at the same point, you've thrown away the use of Wilsonian RG, because Wilsonian RG is something that's important in the continuum world. This is sort of similar to what Natty was stressing in his talk, that you know, things you can do on the lattice don't always translate easily into continuum physics. So in particular, okay, you turn on a 4 fermion term. What do you do with the coefficient of that? Do you make it big? You can't make it small, but you have to make it something precise, or can you make it above a particular threshold? Is it just the 4 fermion term that's important, or should we be including 6 fermion terms and 8 fermion terms? And how many do we really need? And how do we exactly tune all these interactions? The answer is we don't know, and everything that everybody's tried just doesn't seem to work. So I think it's a wonderful idea. It would be great if somebody could make it fly, but at the moment, it's a true statement that nobody's made this idea work in practice. There was a slight diversion into lattice gauge theory. Are there any questions about lattice gauge theory and this story before I move on? Silence. All right. So what we wanted to do in the paper with Shlomo, in part motivated by SPT phases, but in part, I should also say, motivated by this problem of putting chiral gauge theories on the lattice, is find a way to achieve what these people wanted to do, but in the language of continuum quantum field theory. That is, take some chiral fermions and find a way to give them a mass, preserving the chiral symmetry. So let me tell you, sketch how one can do this, and then I'll give you some particular examples. Okay, so what do? You start from a bunch of massless free fermions. And there's a symmetry that's realized on these fermions in a chiral way such that the Toft anomaly is vanishing. And again, in the back of your mind, think standard model and SU3 times SU2 times U1. The idea is the following. Well, firstly, we can't just add a mass because a mass would break the chiral symmetry. And we can't add interactions because the interactions are 4 fermion terms and they're irrelevant. So if we want to find a way to give these a mass, we're going to have to add extra degrees of freedom. So you take your chiral theory, and then in addition, you add extra degrees of freedom that necessarily transform in vector representation, vector-like representation of the same symmetry G. The importance of a vector-like representation is there's nothing that prohibits you just giving a mass to all of these new particles, new fields, and just decoupling them from the system, leaving behind what you wanted originally, what you had originally. Instead, though, you bring the vector-like degrees of freedom down. You allow them to interact with the chiral degrees of freedom so that when you flow to the infrared, everything becomes massive. That's the aim of what we want to do. Let me just flesh out some of those, some of these rules a little more. So what can I do? I'm in 4 dimensions, so what I can add is scalars, fermions, and gauge bosons. And I can add each of them. In fact, I'm going to need to add each of them. But each of them comes with a particular caveat, which I'll tell you about. All right, so firstly, I can add scalars. The scalars can be charged under G if I want them to be. In particular, there's nothing that stops me giving a mass to any scalar while preserving G, so I can always trivially decouple it. The catch is that if the scalars transform under G, you better make sure they don't condense. Because if they condense, they spontaneously break G, and that's not what we want to do. We want to gap these fermions without breaking this group G. All right, next, I could add fermions. However, if I add fermions, I have to make sure the fermions transform in a vector-like representation of G. So I have to add left and right-handed so that I can easily pair them together and give a mass. You know, obviously it would be cheating if I start with some chiral representation of the fermions, add fermions in the conjugate representation, just give them a mass and gap the whole thing and declare victory. That wouldn't be impressive. So the new fermions have to be in left-right conjugate pairs. And finally, I can add gauge bosons. But importantly, if G is a global symmetry of my theory, it's the right way to think about this, I'm not allowed to gauge G when I do this. G has to remain a global symmetry. So if I want to add gauge bosons, I have to identify a new symmetry, I'm going to call H. I can gauge that, but then I need a few requirements. H has to commute with G, and moreover, there can't be any mixed anomaly between H and G. The idea being that once I gauge H, G remains a good symmetry throughout. Finally, as with the scalars and the fermions, I want to find a way to decouple these new gauge bosons so I can return to my original massless fermions. The way I do that is I just add some extra scalars which are charged under H. That allows me to Higgs the gauge bosons H and then decouple them. All right, so these are the rules of the game I've set myself. You know, I think they're very fair rules. We kind of adopted them as the same kind of rules that people talk about when discussing different topological phases of matter. So I think it's the right way to think about things. Any questions about what I've allowed myself to do before I present an example? All right, let me give you...
David, can I ask a question? Hi. There is a very naive, cheap trick I could try, which is to take the usual Higgs VEV to 0 and send the Yukawas to infinity. Now, of course, that's classical, but this would do what you want. Can you comment on this?
It doesn't sound good to me. Obviously we lose control of the theory by sending.
Well, it's strong coupling, of course.
Yeah.
But anyway, you are going to use strong coupling.
Well, you know, I'm going to use strong coupling in the sense that we usually think of in quantum field theory. At the ultraviolet cutoff, everything is weakly coupled. And then you flow to the infrared, and if things become strongly coupled in the infrared, so be it. What you're suggesting sounds rather similar to what the lattice people are trying to do, where you have strong coupling at the UV cutoff. And I explicitly do not want to do that. I want to do, you know, continuum quantum field theory, things weakly coupled at the UV cutoff in the way that we usually think about it.
I see. Thanks.
Hi, David. Another question. For the scalars that Higgs the symmetry H, do they have to be in, say, a nonlinear sigma model into the group H, or could they just be is there any restriction on the topology of the scalar space?
We didn't have any in our paper. There were similar rules that Yuji Tachikawa and Yonakura wrote, where they did require some restrictions on the topology. I don't think we need it here, but I may have missed a trick, actually. So we didn't require it. Yeah, I can't say more than that.
Yeah, my worry is just that if you don't, then you might get other topological symmetries coming from not requiring the scalars to trivialize the gauge bundle.
I see. Yeah, and all we're going to do is we're not going to have nonlinear sigma models for the scalars. They're just going to have flat kinetic terms, but you know, it's just going to be a gauge theory with the usual covariant derivatives for scalars.
Sure,
yeah,
thanks.
We'll write down examples. Other questions? All right, so let me give you an example. It's not the simplest example. We have more simple examples in the paper if you want to look. But for me, at least, it was kind of the example that I was happiest with. It's the standard model. So what I want to do is what I promised before: tell you how to gap one generation of the standard model without breaking electroweak symmetry. Okay, so gauge group of the standard model, obviously. Here's one generation, and I've written them so that every fermion is a right-handed Weyl fermion. In other words, the left-handed fermions have been conjugated, so they're actually right-handed. You can see that, for example, that the left-handed quarks transform in 3-bar, the anti-fundamental rather than the fundamental, because I've conjugated them to become right-handed. All right, so these are the familiar quantum numbers of one generation of the standard model. Notice I haven't put a right-handed neutrino in, but the right-handed neutrino is neutral under everything, so it's trivial to give that a mass anyway. So these are the charged quarks and leptons. Hypercharge has been quantized in a slightly unfamiliar way, so it's quantized in integers rather than in 1/6. All right, so what do I want to do? There's a few steps that will gap all of these while preserving electroweak symmetry. Step 1, I'm going to introduce some new fermions. In particular, I'm going to add 3 pairs of fermions. And importantly, the pairs come in conjugate representations. So each pair, one below the other, these new fermions in red, obviously, I can easily add a mass term for each pair and just decouple them while preserving the symmetry G. Okay, you can see in the left there, +3, -3 of the hypercharge. For the down, the additional ones under the down quark, there's a 3 and a 3 bar. So all of these things just pair together and trivially gap. Having done this, however, the next thing to notice is that there are some representations that are repeated. These are the representations that appear on the first 2 lines. So the representations that appear in the green boxes are repeated. And therefore, in addition to G, SU3 times SU2 times U1, there's a new symmetry, which is H, an SU2 symmetry, under which the fermions in each box transform as a doublet. It commutes with G. You do have to check that it has no mixed anomaly with the U1 in G, but it's simple to check, and indeed it's true. It has no mixed anomaly with the U1. All right. What do I have now? Well, because I've added a gauge symmetry in the system, suddenly I no longer just have 3 fermions, I have a strongly interacting theory. I have SU2 coupled to a bunch of doublets. If you count them, there's actually 6 doublets. There's 2 in the first box and 3 in the second, and just 1 in the third. So it's SU2 coupled to 6 doublets. The next thing to do is to figure out what that gauge theory does. It's a strongly coupled gauge theory, SU2 with 6 doublets. I have a guess about what it does. It's probably a pretty good guess, but because it's a strongly coupled gauge theory, we don't really have full control over it. So the next step is to do something to retain control, which is that I'm going to supersymmetrize the entire thing. So I don't need to do this. Well, we say that differently. I do need to do this, but I only need to do this because I'm not smart enough to solve non-supersymmetric theories. So the supersymmetric theory is solvable. In fact, it's been solved. And so we know what's going on. So what does it mean? It means that I add superpartners for all the fermions that are there. But again, adding scalars transforming under G is legal. And in addition, I add a gaugino, but the gaugino is adjoint under H, but is neutral under G. So supersymmetrizing is also within the rules of the game. What am I left with? This is a slightly busy slide. Let me walk you through it. Firstly, I've given names to all the original fermions. These are the capital letters at the top there, but these capital letters are now capital letters for superfields. Okay. Fermion plus scalar. What I've got at the end of the day is an SU2 gauge theory, supersymmetric gauge theory, coupled to 6 doublets. Now, this is among the class of theories that Natty told us how to solve, I guess 25 years ago now. And this particular gauge theory has a very special property. It's one of many interesting properties that Natty discovered of supersymmetric gauge theories. This one has the property that it confines without breaking the global symmetry. So 6 doublets, the global symmetry obviously is SU6. Importantly though, buried within that SU6 is the symmetry G that I care about. So it was really crucial that if it confines, it doesn't break its chiral symmetry, because breaking a chiral symmetry in this sense is the same as breaking this symmetry G. That would be bad. But I have a theory here which confines without breaking chiral symmetry, sometimes called S confinement. And the low energy physics is all the mesons that I can make from the 6 doublets that are in the green boxes. And there's 15 such mesons. The 15 is because there's an anti-symmetry. So it's 6 times 5 divided by 2 is 15. The 15 mesons are just listed at the bottom of the screen there. Okay, here's the really wonderful thing. Out of the 6 fermions in the green boxes, we generated 15 bound states, massless bound states. These 15 mesons saturate the anomaly of the SU6 symmetry of the supersymmetric theory. Now look at the free particles that aren't in green boxes. There's also 15 of those. There's the 2, and then 6, and 1, and 3, and 3 going across from left to right. The really nice thing is that the quantum numbers of the 15 fermions that are left untouched under SU3 times SU2 times U1 are exactly conjugate to the quantum numbers of the 15 mesons that are listed at the bottom of the screen. In other words, what I can do is I can go back to my original theory. I can add a superpotential term which just pairs the mesons coming from the green boxes with the fermions that aren't in the green boxes in such a way that the symmetry G is preserved. So what does it do? Well, this superpotential is marginally irrelevant in the UV. It's Yukawa terms for the theory. But as you flow to the infrared, this turns into a dangerously irrelevant operator. So this is irrelevant in the infrared. The mesons bind together into new composite fields, and then this is just a mass term for everything in the infrared. So this is a simple system which now gives a mass to all the fields, but it gives a mass to all the fields while preserving SU3 times SU2 times U1. It does what we want it to do. As I said, I invoked supersymmetry. I invoked supersymmetry as a crutch just because I know that these supersymmetric theories have this particular property that Natty discovered. Probably supersymmetry isn't necessary. So what you really need is an SU2 gauge theory that couples to 6 fundamentals that does not break the SU6 chiral symmetry. And I strongly suspect that what I've written down here does the job. So this is actually the supersymmetric theory, but where I've just thrown away all the scalars. There's certainly a fermion that's made from the adjoint and 2 fundamentals, a composite fermion, which saturates all the Toft anomalies in the infrared. So it seems very plausible that, that this theory here confines, but with massless fermions in the infrared without breaking SU6. This also would then do the job I explained previously. In fact, there's a large N version of this. In fact, you all know the large N version. It's a chiral theory, SUN, with a symmetric and N+4 anti-fundamentals that believed in the large N limit to confine without breaking the chiral symmetry. This was suggested in the paper listed at the bottom here. Okay, this is the N=2 version of that theory that turns out to be non-chiral as an SU2 theory. All right. That's sort of one of the punchlines of the talk, how you gap fermions while preserving a chiral symmetry. I have a slightly different topic just to finish off, talking about a discrete symmetry. But any questions before I change topic?
Yeah, if I may.
Hello, Zohar. Oh, Natty. Hello, Natty.
Yeah. Hi, David. There's a weaker statement that is, I think you did prove, that this system satisfies the same anomalies, including maybe even anomalies you didn't think about.
The one on the screen at the moment?
That's right.
Yes.
So there's a dynamical question of whether a particular system indeed gaps it or not. But I think what you did prove is that it has the option to gap it.
That's absolutely.
Therefore, even that system, even if this system does not do the job, it's quite reasonable that there is a deformation of it, which preserves all the symmetries that does do the job. So this is a slightly weaker statement, but I think that you rigorously established. So I wonder whether you agree with that summary.
Yes. Yes.
Thank you.
Although what you said one thing, there may be other anomalies that I didn't think of. I don't know of any for this. I know of some for closely related things, but I don't know of any discrete anomalies in this particular case.
No, but imagine somebody comes up with some fancy math that determines that here's some another anomaly, I don't know, mod 6 or whatever, who knows? We didn't think about. I think your construction, assuming that the supersymmetric theory really does what it does, guarantees that that cannot be the case.
That's true, but and as you know better than anyone, and I think I learned a lot of this from your talks. You know, our lattice friends make the kind of arguments that you just made, and they have this horrible phrase: the theories live in the same Hilbert space, which is just, you know, a stupid thing to say, but I think we know what it means. They share the same anomalies, and then they sort of say job done. But the job isn't done, as we saw from the Eichton-Preskel analysis. You have all these couplings on the lattice that you have to tune to very specific things, and you don't really know what you have to tune them to. And the beauty of continuum field theory is that you just have a handful of operators that you need to tune. And so I don't want to say it's possible this happens. I want systems where I know it happens, where I know what's going on.
Exactly what I discussed in the panel discussion in the spring meeting in Amsterdam. It's exactly the question you alluded to, including the phrase in the same Hilbert space, which I don't know what it means, but I tried to give meaning to that. And I think the statement is that there's a bigger space of deformations, that within that bigger space of deformations, you can indeed gap it. Now, continuum field theories are interested in a smaller space of deformation, then it's not clear whether you can or cannot gap it. But within the bigger space of deformations, I think it's quite clear.
I completely agree, but the hope is here that we can say, you know, you can do it in the continuum where you really have control, and supersymmetry brought us that control. To finish that, let me just tell you about a.
David, I had one more question.
Oh,
just
go ahead.
A very small technical question. You mentioned that one of the rules is that the fermions that you add must be decoupleable. How I don't see that happening in the way you added the new fermions. You added vector-like fermions, but then you gauge the SU2, and I don't see how to decouple the stuff that you added. So I don't understand why it's in the same class. Like, how do you even prove that you can flow to the standard model here now? You can't decouple the stuff anymore.
I can decouple everything. I've only added the gaugino. I can just give a mass term for that. That can decouple trivially.
No, but like maybe I'm missing something stupid. Like you added this 1,2 minus 3, and then 1,2 plus 3, right? But you can't anymore.
I see. No, I can. All I have to do is add a Higgs field for H, and then I can do it. So what do? I have a Higgs field for. Can you see my cursor?
Yeah.
So I write down a mass term for these. That's now charged under H, but I also add a Higgs field for H. Turn on that Higgs field. It does two things. It gives a mass to those objects, plus it Higgs is H.
Yeah. So, okay, but that's within the rules, I guess, of what you're allowing to do.
So that's absolutely, the rules are I have vector-like stuff and I've got to find a way to decouple it. And here we can.
Okay, fair enough, thanks.
Let me tell you a slightly different story. It's a bit weaker actually, but it's been fun learning a lot of this stuff. And so this is partly for pedagogical reasons. Four-dimensional gauge theories, or four-dimensional field theories, I should say, have a wonderful and I think remarkable discrete anomaly that's analogous to that Z8 anomaly I mentioned in the Fitkowski-Kitaev story. So the symmetry is the following. It's what's called a spin Z4 symmetry. So it's a Z4 symmetry, but the word spin means that the generator of the Z4 symmetry squares to fermion parity. So it squares to -1 to the f. In particular, that means that if you have a fermion, this Z4 has to act as either plus or minus I on the fermion. But if you have a boson, this symmetry has to act as plus or minus 1. So it squares to -1 to the f. And there's an anomaly associated with this symmetry. It comes from these borders and groups. And the anomaly is a Z16 anomaly. So in particular, the anomaly is counted in the following way. You just count up the number of fermions that transform with a plus sign, that's n plus, and then you count up the number of fermions that transform with a minus sign, that's n minus, and you just take the difference. So again, it doesn't take much to see that if you have a theory with a non-trivial nu4, for example, 2 fermions both that transform with plus I, you can't write down a mass term. It would not be invariant under this spin Z4 symmetry. So it's a discrete symmetry that prohibits writing down a mass term for the fermions, and has this mod 16 anomaly. The fact that it has a mod 16 anomaly means there should be a mechanism to take 16 of these fermions all together and give them a mass. So the question is, what mechanism can we have in 4-dimensional field theories that achieves this? I should point out that this spin Z4 anomaly was I think first discovered by Tachikawa and Yonekura in a paper about orientifolds in string theory. But a clear description in a field theory language is in this nice paper by Garcia, Estebaria, and Montero. All right, so this is the question that I just phrased. Can we write down a theory in 4 dimensions that has this spin Z4 and gaps fermions in groups of 16? Well, the answer is yes, but there's a twist that makes it a little bit trivial. Let me tell you the theory that does it, and then we'll see why it's not quite as clear cut as I would have hoped. So the theory, by the way, I have supersymmetric theories that do this. This is a non-supersymmetric example where, again, we think we know the dynamics. We're not entirely sure, but we think we know the dynamics. And it's a theory that was studied in the early 1980s, SUN gauge theory with an antisymmetric a Weyl fermion in the antisymmetric representation and n-4 Weyl fermions in the anti-fundamental representation. This is designed so that the SUN anomaly vanishes, so that this is an anomaly-free chiral gauge theory. And then in addition, I'm going to add a bunch of singlets, and I'm going to add this number of singlets, and we'll see shortly why that's the right number to add. Okay, so this is the theory. Now I'm going to write down a 4 fermion term. 4 fermion terms we think are irrelevant, but it's going to turn out this 4 fermion term is dangerously irrelevant. So it's actually going to be important in the infrared. So I've told you what the various fermions are. Psi are the anti-fundamentals, lambda is the antisymmetric, and then the bunch of singlets I call chi. And this 4 fermion term, there's a unique way to construct it so that it preserves the SUN-4 global symmetry of the original theory, together with a non-anomalous U1 global symmetry of the original theory. And I'll tell you what those U1 charges are on the next slide. Notice that the way this happens is all of those singlets, they're singlets under the gauge group, but they rearrange themselves into the symmetric representation of SUN-4. And that's why I have the particular number of singlets that I have at the top of the screen there. All right, so what happens? Well, this theory was conjectured 40 years ago to confine, without breaking the global symmetry, with a massless fermion, massless composite fermion emerging in the infrared. There's also good large n limits there's also good large n arguments that it does this rather than anything else. So it's thought to leave behind a massless composite fermion, this thing I've called chi tilde here, that transforms in the anti-fundamental version of the symmetric representation of SUN-4. In particular, if this is the dynamics, then the 4 fermion term that I've written at the bottom, at the top of the page there, that's in the UV. As you flow to the infrared, it just becomes a mass term for the composite fermion plus the singlets that we had originally. So this is another simple model that is thought to give mass to all the fermions, now while preserving an SUN-4 times U1 chiral symmetry. Okay, what does it have to do with our discrete Z4 symmetry? Well, it turns out that I've written the U1 charges, the non-anomalous U1 charges at the top there. It turns out that if n is odd, and only if n is odd, this U1 symmetry has a spin Z4 subgroup. The spin Z4 subgroup acts as all the fermions go to plus I, none of them go to minus I. Now, it is possible to add other fields, in particular just add some scalars into the game, and add lots of other terms, Yukawa terms and such like, so that the U1 is broken, but the spin Z4 remains. So you can sort of cook up a theory that has just the spin Z4, not the U1. But you're kind of doing it just to make a point. Ultimately, this Z4 is living in a U1. The nice thing is that you can now compute the index. The index is just the sum of the number of fermions. I've written it down there. It's not 0, but it is 0 mod 16. And it had to be 0 mod 16 because this we've seen these fermions are gapped while preserving these symmetries. So it's sort of an example where you can gap fermions preserving the discrete symmetry, but it's a bit of a swizz because the discrete symmetry was really buried inside a U1, and if the anomaly for the U1 vanishes, you can show that the anomaly for the Z4 vanishes mod 16. So it's a little bit more trivial than I would like. All right, so that's the end of my talk. The summary is very straightforward. You might think that you can't gap fermions preserving a chiral symmetry because left and right transform differently. That's a true statement only at weak coupling. If you allow any strong coupling in quantum field theory, the only obstacle to gapping fermions is not the chiral nature of the symmetry, but is the vanishing of the Toft anomaly. That's the punchline. All right, thank you for listening.
Okay, let's thank David for a very nice talk. Questions and comments?
Yeah, can I ask a question?
Go ahead, please.
Sorry, can I ask?
Yeah, go ahead, please.
Yeah, so very nice talk. So I was wondering if a strong coupling, for instance, we can gap out one generation of the standard model. Is there any sense in which it could be that in the real world, the generations that we observe actually have small masses or something like this? They're not actually completely gapless? Or more generally, how can we ensure that the standard model, that the stuff in the standard model is really gapless?
I didn't understand the second question. I'll answer the first, and then we'll come back to the second. You can see if the mechanism I've given here could possibly be phenomenologically viable, in the sense that maybe there could be a small contribution to the first 3 generations through this way. That's not possible because you would just see these extra fields, and I think actually the fermions would couple in such a way that it's not possible. It is possible if there's a 4th generation that could have a mass through something like this, but I believe it's not phenomenologically relevant for the first 3. What was the second question?
Well, it's just a big question that how sure are we that the stuff that looks massless, like the photon or like the generations, how sure are we that it's really massless? Because one argument that you typically give is like chirality with coupling, but I'm just wondering how strong is that? It's like just a big general question.
Yeah, and none of the fermions are massless in our world, so
sure, but sure, but we understand why, right? Like they are massless at the electroweak scale. The photon's massless, for instance.
Yeah, I have no comment about masslessness of gauge bosons.
Right. Thanks.
Other question?
One question, David.
Go ahead.
Yeah. You didn't speak about 16 fermions in 3D with time reversal symmetry.
Yeah, that's right. Oh, you want me to speak about it?
No, just if you have a gauge theory that lifts it.
Oh, we do. But Witten does as well. So in 2016, in Witten's paper that has parity in the title, and maybe anomaly, inverted commas, he has a very nice and very simple U2 gauge theory. I could probably even tell you. I think it's U2 gauge theory coupled to I'm gonna screw it up, but it's U2 gauge theory coupled to a bunch of fermions. You give the fermions a mass through a Yukawa term. So there's sort of a psi phi, and there's a psi phi, and the psi is such that it's gauge invariant under SU2, but has charge 2 under the U1. So the Higgs field has to have charge -2. The Higgs field naively seems to break time reversal symmetry when it gets a VEV, but there's a new time reversal symmetry that you can define, which is a mix of some gauge rotation and the old time reversal. In fact, this same trick is in a previous paper by Natty and Edward. I'm a little unhappy with this example, I have to say, because the anomaly in 2 + 1 dimensions is for time reversal that squares to -1 to the f. And by the time you do this twist, it squares to +1 to the f. So I don't really think you managed to gap fermions preserving the time reversal that had the algebra that you should. And actually, if Natty has some comments on it.
For t squared equals +1, there's a z2 times z2 anomaly too. It's not z16, it's something else.
Well, nonetheless, this is 16 fermions, and it's advertised as gapping them while preserving that t squared, and ultimately it doesn't. In the paper, we also have, I think, quite a cute supersymmetric theory that gaps while preserving time reversal, where the anomaly vanishes. Has exactly the same problem, though. If you look at the time reversal after the breaking, it gets a twist with another operator and squares to +1 rather than -1. So I don't actually know of a system that gaps 16 fermions in 2 + 1, preserving t squared equals -1 rather than t squared equals +1.
One other question. It seems an important part of your story is the Higgs fields that I asked about before, right? Because you want to start with the phase that you began with, where you should Higgs away the gauge fields. Presumably, you then you make the Higgs massive so it doesn't break the symmetry. And my question is that maybe it's obvious, but I guess I would worry about the Higgs in this new strong coupling phase, which gaps the fermions. I would worry about the Higgs being light.
Because it may condense and therefore screw up G. Is that?
Well, I'm just worried. I'm just worrying that it, can you take it into account to make sure it doesn't screw up the picture in the strong coupling phase? So it's very important that it's there in the weak coupling phase.
So just so I understand, Jake, yeah, okay. So here's all the ingredients that I need. Are you worried in particular about the super partners of the fermions?
No, I'm worrying about the Higgs field that allows you to gap out all the right. You need to have it so that you can gap out all the other degrees of freedom trivially.
The Higgs field that will allow me to gap out the H equals SU2 gauge bosons.
Yes, exactly.
Yeah. You actually can identify that with the super partners of the
Sure.
Of the fermions. You've got to decouple the Yukawa coupling between them, but then you yeah. So there is a concern that this condenses, but we know from the solution of the supersymmetric theory that it does not.
I see.
And of course, if this theory does what it's conjectured to do, then you actually don't need any scalar fields. Actually, that's not quite true. For the reason that Zohar asked, you do need the scalar field still to break the SU2.
Right. You want to start in the phase you started. Yeah.
Yeah. But again, in the phase where you're doing what you want to do, the strong coupling phase, you can just give that Higgs a very large mass.
Sure. That makes sense.
Just decouple it. Yeah.
Other questions, comments?
David, I have a bit vague question. Is there a way to do this in a way, coupling to a holographic theory and some holographic way of generating these masses using strong coupling?
I haven't thought about it at all. Yeah, I don't know. I don't know. You take some 5-dimensional theory. I don't know. Yeah, it smells like there should be a story, right?
Yeah, the reason I asked the question is that somehow if there are some kind of weak coupling picture in the gravity side, you might be able to have some kind of analogous of topological classification of the mass terms. Just something vague, like you have in, like you can, in the weak coupling picture, you just have this standard classification of topological phases based on how many, just a free fermions, how many mass terms you can write down and study the topological properties.
No, I think it might be trivial. I think it might be trivial in the following sense. You have some symmetry G on the boundary that doesn't have a Toft anomaly. So there's gauge bosons G in 5 dimensions, but I think the fact it doesn't have a Toft anomaly means there's no Chern-Simons term associated to them. And then if you want to gap things, obviously you put an infrared wall there, but the fact there's no Chern-Simons terms means there's no problem with just putting trivial boundary conditions on the gauge fields on that infrared wall, I think. So it sounds like it might just be a very straightforward observation from the perspective of...
Right. Thank you.
Okay, other questions and comments? So, Ayan, if not, should we close the session?
Yes, of course, we have to sleep.
Great. Let's thank David again for a very nice talk.
Yeah, thanks to all the speakers, and welcome all of you to Chennai. Please visit us sometime. And David, especially if you come to India, you cannot miss Chennai.
I'll come for sure, guys. Yeah.
Okay. Goodbye, and and see you tomorrow for Tom Rudeli's talks. Bye.